and once we have an integral operator, then we can see its property and we can apply the some suitable pointer for that operator. So I welcome sir again, and I request sir, so please.
Thank you.
Give your talk.
Thank you. Okay, so as you have seen in the last lecture, I had discussed the basic that contraction principle and its extensions. So now, as promised, I am going to discuss its applications to differential equation. So in differential equation, we have two types of problems: initial value problems and boundary value problems. Okay. So let's start with an initial value problem. So usually all practical problems are of even orders. Of course, for completeness sake, we get odd order differential equation, and in certain problems you may encounter those odd order problems, but in most of the applications you have second order problems or even order problems. So let's take a very simple case like this. Sorry, y prime. I will not consider that y prime term, but you can in general include that also. So because we are talking about very simple examples here, and so here x is greater than 0 or x can be greater than some point x naught, but for simplicity we will take the starting point as 0. Okay. And then you have two initial, because it is a second order, so you have two initial conditions, that y 0 equal to a and then y prime 0 equal to b. Okay. So as you know, we are going to consider the applications of this fixed point theory. So we will convert it to an integral equation, and here, so what do we simply integrate those derivatives. So first integration will lead to this y prime x equal to y at 0 is a, and then you have plus integral this 0 to x f t dt, and then you have minus lambda 0 to x y t dt. Okay. Sorry, this should be b, y prime at 0 is b, and then second integration will give us y x equal to a plus b x plus, you have now double integral 0 to x and then 0 to t, and then f s ds and then dt, like that you dummy variables keep changing. So 0 to x again, and then 0 to t y s ds and then dt. Okay. Now to get rid of these double integrals, we use the theorem. In general, what we have is like this, that 0 to t and 0 to 0 to, let us say, x and 0 to t and some function. It may be a function of x also, t and s and then ds and then this dt. This you can see that this is actually equal to 0 to x and then s to x f. The change of order of integration will lead to this, that x t s, and now dt goes inside and ds comes outside. Okay. This is standard result in the change of order of integration, because you see what we are doing here, you have like this one inner variable initially, you have s and then you have t here, and then this is the line t, diagonal line t equal to s. Okay. And then there is upper limit 0 to, this one is x and x here. So this is, you see that t variable goes from 0 to x and then s goes from this 0 to t. So this is the kind of region where we are, this is the region where we are integrating. this this triangle. Okay. So when you change the order of integration, you go strips go like this. Okay. So again this s will go from 0 to x, and then t will go from this to this. That means s to, because this line t equal to s to x. Okay. And the function remains the same there. Okay. So now this one will then, using this, will get converted into, so if you remember what we have, so I will just simply use this one. I drop this. So the change of order of integration will lead to this a plus bx plus 0 to x, and now s goes out, t comes in. There is nothing there with as a function of t. So you what you will have is simply this s to x and then dt, and you have fs ds, right. So this will give me simply x minus s. So x minus s fs ds, and I can then change this s to t, because those are dummy variables, like this. And same thing goes with that lambda 0 to x and then x minus t yt dt. Okay. So here this f is a known function. So overall this is some function gx and then minus lambda 0 to x and some function kxt yt dt. Okay. So what you have is finally this equation. So that is a Volterra equation, and here kxt is nothing but x minus t. Okay. X minus t here. This is everything is a function of x, which we write as gx here. Okay. So that is a Volterra integral equation. Okay. So an initial value problem, you may have now certain even nonlinear terms here. So there may be a nonlinear kernel coming there inside whenever you have initial value problem there. Okay. Now for a boundary value problem, so if you take this y double prime plus lambda y equal to fx, and now this equation is to be satisfied inside this 0 1, let us say, for simplicity, and then you have certain boundary conditions that y is 0. Again, boundary conditions can be very complicated also, but we will take very simple condition, endpoint conditions, that y 0 is a and y 1 equal to b. Okay. Usually you have an SLP, then you know the general SLP is like that you have certain r there, rx y prime prime plus qx plus lambda rx y of x equal to 0, and then you have boundary conditions like k1 y a this 0, or you may have a less than x less than b, and then y a plus k2 y prime a equal to 0, and L1 y b plus L2 y prime b equal to 0. That is a general SLP. So it's a particular case of that SLP there, right? Here these may also be non-zero kind of things there, and you may also have certain periodic conditions also, like here you may have that y 0 equal to y at 1. These kind are called periodic boundary conditions. So those are not included here. You have those are separate periodic boundary value problem. But for simplicity, we will deal with this. Now, how to convert this to an integral equation? We follow the same procedure and see what we get. So, again the first integration will lead to that same one, that y, of course, we do not know y prime 0. So, y prime x equal to y prime 0 and plus integral 0 to x f t dt minus lambda 0 to x y t dt. Is that okay? And now again integrating it, so you get y at x. Now y 0 we know, so y 0 is a and plus y prime 0 x plus these things you get in the same way, 0 to x, x minus t f t dt and minus lambda 0 to x, x minus t y t dt. Okay. So, this is the unknown here, we have to find. Okay. And for that we will use this condition is already used, we now use this one, and so substitute y x equal to 1. So, y 1 is b. So, we get b equal to a plus y prime 0 plus 0 to 1 1 minus t f t dt minus lambda 0 to 1 1 minus t y t dt. Okay. And so, now y prime 0 is determined from here. So, that is y prime 0 is b minus b minus a minus 0 to 1 1 minus t f t dt and plus lambda 0 to 1 1 minus t y t dt. So, substituting that here, then we will get the corresponding integral equation. So, let us see that. So, what we have is now y x equal to a plus substituting. So, you multiply this by x. So, this is into x here and x here. Okay. So, a plus b minus a into x plus sorry, this is minus here, minus 0 to x, x into 1 minus t f t dt plus lambda 0 to x, x into 1 minus t y t dt, and then the remaining terms there, plus 0 to x, x minus t f t dt and minus lambda 0 to x, x minus t y t. Okay. Now, so this looks like a very complicated one. We want to simplify it. We break these, sorry, it was 0 to 1, 0 to 1, okay, 0 to 1. Now, we break this integral to two parts, 0 to x and x to 1. Okay. And so, 0 to x will be added to this, and so what it leads to the following, that you have a plus b minus a into x, and then you have with f t we will. So, how we write that? I will write that like this, 0 to 1 and some function k x t f t dt, and then plus similarly for the other one lambda 0 to 1 k x t y t y t dt. Now, recall that from x to 1 it is simply this, and for 0 to x this this minus that. Okay, and it's a simple calculation actually, that this k x t comes out, and same thing happens for that also with the minus sign. Plus becomes minus or minus becomes plus, like that. So this is actually the kernel. This is t into 1 minus x whenever this 0 less than t less than x less than equal to 1, and this is x into 1 minus t whenever 0 less than x less than equal to t less than equal to 1. Okay. So, and this part is simply your okay, the whole thing you can write it as gx, and this is the integral operator part. So, what we got now is a Fredholm integral equation. So, we get now this y of x, or now I will write it as phi of x equal to f x, or so all that gx I will now write as f x plus lambda 0 to 1 k x t y t dt. Okay. So, this is a Fredholm integral equation. All right. So, whether we have an initial value problem or we have a boundary value problem, correspondingly we have respectively either this Volterra integral equation or Fredholm integration. Now comes to the main point that how do we apply this fixed point theory. Okay. So, now so for that the unnecessary details we suppress and write it as an operator equation. So, what we need to solve is this phi equal to f plus lambda, and this we write it as operator k of phi. And what is that operator k? K phi at x is, in the Volterra case it is 0 to x, or we can write it like this also, 0 to 1 k x t phi t dt, where in the Volterra case this kernel k x t is simply that, let me write it as k1, it is simply that k x t, okay, when and for 0 less than x less than equal to t, and it is 0 for this less than equal to 1, and 0 less than equal to t less than equal to x less than 1. So, the other part it is 0, and for so it is in the Volterra equation case it is like this, and for the Fredholm equation it is simply k1 x t is over that k x t, right? Is that right? And here that k x t in that Volterra case maybe is different. So, let me okay, let me not get into the complicated thing. For Volterra we have like this, where this is k1, and for Fredholm it is actually over this k 0 to 1 k x t phi t dt. Okay. Now, so so we look at this operator equation and we define the operator t. Now, we have to first specify where we are going to consider this. Okay. So, the simplest one would be when we have this x as c 0 1, uniformly continuous functions, the space of that, and the norm, you know, that supremum norm is considered there. And so here we we have these functions also continuous, and this function f is also in the, this is actually from k is from then 0 to 1 cross 0 to 1, and it may be in general a complex number. Okay. And so these are also, this space is complex valued continuous functions. So it's a complex Banach space. Okay. Now here, okay, so we define this T from this x to x like this, that T of phi equal to f plus lambda k phi for any phi in x. So now we look at t to the power n here. What happens to that? Does it converge or not? Huh? So that's where, if it or is it a contraction or not? And if it's a contraction, then we know from Banach contraction principle that it will converge to a fixed point, unique fixed point, phi 0. Okay. So let's look at the sequence Tn. So you have now, let's say, t square of phi. So t square of phi is f plus lambda k. T square of phi is t of t phi. Okay. So here you have to simply replace this t phi and substitute that t phi there. So you have f plus lambda k of f plus lambda k phi. You see, even though k is a linear operator, t is not a linear operator. Okay. So there is no restriction of linearity there. You can go to even nonlinear kernels there. Under certain restrictions, we will have our result for that too. So continuing this way, what happens here? So this actually comes out this f plus lambda kf plus lambda square k square phi. So by this it keeps on shifting. So t to the power n phi will then be f plus lambda kf plus lambda square k square f and so on, plus lambda to the power n minus 1 k to the power n minus 1 f plus lambda to the power n k phi. Now k is an integral operator. How do we see that? What are these k square, k and so on? Are they also integral operators or not? So it happens that they are also integral operators. So let's see that. So this is true whether you consider the Volterra equation or Fredholm equation. Okay. The only thing is, when you consider the convergence part, that's where now things will differ. And you see that what is t square. So if k is what is k square? So k is like this, k phi of x in the Fredholm. Now we will first consider Fredholm and then we will deal with the Volterra. So 0 to 1, this k x t phi t dt. Now k square of phi x, then it will be 0 to 1 k x t, and here k phi t dt, right? And so now just substitute that k phi t. So 0 to 1 k x t, and here then 0 to 1. Now we'll have to change the variables, that k t and let's say s, and then you have phi s ds and then dt. Okay. So now the change of order of integration will give us this 0 to 1, and then so this s goes out, so phi s will go out, and you have this 0 to 1 k x t and then k t s and then so dt and then phi s ds. Okay. So, I just to keep things in a simple order, what we do, we just change the dummy variables. So, we will write this as s, interchange the t and s. Okay. So, s here and t here and ds here and then phi t dt. Okay. Does not matter, those are dummy variables, you can rename them in any manner you like. So, this k square, this is the kernel of k square. Okay. So, we write this as k 2. So, we will have this k 1 x t is simply k x t, whatever kernel we have there originally, and then k 2 is this. So, k 2 x t is 0 to 1 k x s and then k k x s and then k s t d s. Continuing this way, we will have now since k square is the integral operator. So, again you take k with k square, that is repeating the same process, it will also be an integral operator, and you then have these kernels. So, this k n plus 1 x t is the kernel for k n, this is the kernel for k n plus 1 operator, which is 0 to 1, and then you have you can write k n here, or I mean let me first write that, and then k x s and then k n s t d s. And by symmetry you will see that whether you write n here or here, it does not matter, it is the same thing, that 0 to 1 is k n x s and k s t d s is the same thing. Okay. So, it is not that you have to remember you write k n here or here, it does not really matter. Okay. So, those are all integral operators, and so continuing this way, what we get finally the following series, that is called Neumann series. So, here so what you have is then as n tends to infinity, what you will have, if we by some way we ensure that this t is a contraction, then it will go to some phi 0, and that phi 0 is going to be a solution there, right, because if phi 0 is a fixed point, then you see that t phi equal to phi, and then phi equal to let us say phi 0 is a fixed point, then phi 0 equal to t phi 0, which is nothing but f plus lambda k phi 0. Okay. So, then phi 0 is the solution, right, and it is a unique solution for that, provided this t is a contraction. Okay. And we will see that under what condition this turns out to be so, or later on we will see that t to the power n is a contraction, and then by that generalized result we will have a fixed point of t, which again then gives a solution, and it will be a unique solution for that integral equation. Okay. So, let us see now what we are getting, that then this phi 0, in case it is ensured that we get such a phi 0, then you have that phi 0 is f plus lambda f lambda k f plus lambda square k square f and so on. Okay. So, this if you write it in an integral form, what you get is this phi 0 x equal to f x, and then you take out that one lambda, and then you write these are for Fredholm it is 0 to 1, and then the first one is that k 1 x t, and then here one lambda is gone out, so plus lambda of k2 xt and so on, and then you have ft dt. Okay. So, provided this series of kernels converges, then what you get is the following, that f of x plus lambda 0 to 1, this is called resolvent kernel. It is like this because it is a function of lambda also, lambda and xt and ft dt. The solution phi 0 is given by this. Okay. Now, everything is known here. This provided this converges, you know that limit is that resolvent kernel, and f is known here. So, phi 0 is known by that. So, you need to just get that this sum of these no, this series you have to sum up in order to get the solution. Okay. Once we are ensured that this T is actually a contraction. So, let us look at that when it is going to be a contraction, at least in the Fredholm case, and then we will see that in Volterra case it is much more simple. There are no restrictions on lambda as such. Here this we will see that for a small lambda this series will converge, and for that you see that here what you get is this series that f plus lambda kf, okay, plus lambda square k square f and so on. That so you know that it is something like if you ensure that mod lambda norm k is less than 1, then this series will converge. Okay, and it will actually be, it is the expansion of identity minus lambda k inverse of f. Okay. So, this this will exist provided this condition is satisfied. Okay. So, this and actually what you know is this norm of that little k 0, because you know the kernel, and so you may have to get a slightly more restricted one, this one, that mod lambda to norm of little k 0 little k of this is L2 of 0 1 cross 0 1. Okay. And this is simply the operator norm 0 L2 0 1, that, right, operator norm. So, the condition is for a small lambda, you are ensured that this is indeed so. Now, let me look at the Volterra case. So, for Volterra case we have these kernels like this. So, again, so our operator, Volterra operator k phi at x is equal to 0 to x, that k x t phi t dt, and so k square phi at x will be then 0 to x k x t k phi t dt, and this 0 to x k x t, and then 0 to t you have k t s phi s ds and then dt. So, change of order of integration, recall what I have explained there, you will get 0 to x, and you get that s to x, okay, and you have k x t and k t s going inside dt, and then phi s ds. So this is again I change these dummy variables. We write it as t to x and s here and s here and t, just interchanging t and s. So this is the kernel for k square, okay, and likewise you can get the higher order kernels. Okay, so then what we have is for this general one is that k n plus 1 x t equal to t to x k x s and then k s t ds, and here or here really doesn't matter. Now we need to get certain estimates on this. So what we have is the following estimate, that k n x t will be let us say that k x t is a continuous function, the original kernel. Later on we will relax that and we will take the general L2 kernel. For the time being, let us take that k, because for that particular example what it was, simply k x t was that t into 1 minus x for t less than equal to x, and x into 1 minus t for x less than equal to t. At least for that case this is a continuous function, right, and on this compact square it will be bounded. So let us take that this k x t bounded by m. So k x t is less than equal to m for all x, for all 0 less than x, t less than equal to 1. So then what do we get? So we will have actually so there is this estimate m to the power n x minus t to the power n minus 1 over factorial n minus 1. I think that is what I should get. Okay. So let us see this. So of course for n equal to 1 you have that there, for 2 n equal to 2 we have this one here k2 is like this, and what you get is okay, m square there and x minus t ds, right, and times norm of phi there. You actually have to okay, so let me okay k2, let us look at k2 xt mod. So that is actually equal to mod of y2 x k x y, and then mod of this, mod of k x t s and k s t and d s. So m square comes out into x minus y simply. So that is also okay for n equal to 2, n equal to 2, right, that matches. Okay. And so by induction let us suppose that this is so, and then you apply that here. So you have mod k n plus 1 x t is less than equal to then m to the power n plus 1, and you have t to x and s minus t to the power n minus 1 factorial n minus 1 here, and ds. Put this equal to u, and then at lower end it is 0, at upper end it is simply okay, x minus t and to the power n, and one more n here, and that matches with that. Okay. So, you have this estimate. All right. Now, we will look at this t to the power n. What happens to that t to the power n? Is it a contraction or not? Because that in the Fredholm case, we had taken mod lambda less than 1, and you know that I have already shown that in the last lecture, that for small lambda in the Fredholm case, that is a contraction, and that is how we have got that phi 0 there. Okay. Now, in this case, do we need any restriction on lambda? We will see that now. So, t to the power n phi is what? Recall that it is f plus lambda k f plus so on plus lambda to the power n minus 1 k n minus 1 f plus lambda to the power n k n phi. Okay. So, now looking at this difference phi 1 minus t n phi 2. So, that the first part cancels, that is common in both the things. So, you have lambda to the power n k n phi. This is a linear operator. So, you can write, or does not matter, you write it as k n phi 2. Okay. So, now we need to take the norm of that L2 norm. So, let us look at first this t n phi 1 x minus t n phi 2 x. So, that is less than equal to mod lambda to the power n, and then you have mod k n phi 1 x minus k n phi 2 x. Okay. So, squaring that square there, and then integrating it 0 to 1 and 0 to 1, then dx there, and substituting all that. So, it will be mod lambda to the power 2 n 0 to 1, and this k n has the kernel, that little k n. So, k n x t, and you have this phi 1 x minus phi 2 x mod of that dx, sorry, t dt, and then you have integral 0 to x there, right, and then finally dx. Now, so use the Cauchy-Schwarz there. Okay. So, you will get so mod lambda to the power 2 n, and then you have 0 to 1. Inside 1 you use Cauchy-Schwarz. So, you will have 0 to x mod k n x t square dt, okay, and square is also there. I forgot to put that is square there. So, that is square root will disappear, right, and then you have this norm phi 1 minus phi 2 square, okay, dt, and then dx there. Now, we had that estimate there. So, you putting that estimate here, and okay, so you will have that m to the power 2 n mod lambda to the power 2 n, and that factorial n minus 1 square you will get, and then you have 0 to x, then x minus t to the power n minus 1 dt, and then norm phi 1 minus phi 2 square. Now, this you can see that okay, yeah, oh sorry, e to the power 2n minus 2 like that. So, this quantity is anyway less than 1, you can ignore that, and 0 to x dt. So, this part is going to be bounded by 1, you can forget about that. And so, now taking the square root, you will have this m to the power n. So, our this norm t n phi 1 minus t n phi 2 is less than equal to, then taking square root, then you will have this lambda to the power n over n minus 1 factorial norm of phi 1 minus phi 2. Okay? Is that clear? So, now because of this factorial term here, choosing n sufficiently large, this quantity you can make less than 1, okay, without any restriction on this lambda. You choose a large n and you get this less than 1. Okay. So, so this is some k there which is strictly less than n. Okay, k n you can put some k n for that, you take a large n and fix that n, so that this k n is less than 1, okay, whatever that k n is here. So, it is a contraction, and therefore, it will have a fixed point, and then you have this same Nyman series converging to that fixed point. Okay. So, that actually gives us the solution. Now, let me see some more, because yeah, I have some half an hour. So, let us look at some examples. So, if you consider this example, example 1, that phi of x minus phi of x equal to 1 plus lambda 0 to 1 x y phi y or x t y t dt. Okay. So, now our k1 x t is simply x t. Okay. So, you to get that, what is that phi 0 there, you need to just take that sequence k n and see whether it, for what lambda it sums up, and so you have, I think it is 0 to 1 only, no, yeah, 0 to 1. So, there will be a restriction on lambda naturally, because it is a Fredholm integral equation. So, you calculate k 2 x t, and what is that? K 2 x t is 0 to 1, and k x x s and k s t d s, which is 0 to 1, and this is x s, and so x t comes out, and then you have s square and d s. So, you get x t by 3. Okay. X t by 3. So, this thing will keep on repeating. Let us look at one more, that k 3 x t will be 0 to 1, k x t is that x, k x s is x s, and then now you have again this s square. So, x t by 3 will come out and ds, and then you get one more t there. So xt over 3 square, and like that you will get that series in 3. So what phi will then finally be, you can see that you have where does it, x somewhere is cube by 3 only, no? Why it is getting 2 there? Is something I am missing or what? See, phi x, that fixed point actually comes out, or phi 0, it comes out to be 1 plus that lambda x over 2 summation lambda to the power lambda by 3 to the power n. Maybe I lambda and yeah, to put that lambda also there, right? K2, K3, okay. So x t by 3. K1 am I doing something wrong? Kx, yeah. This is okay as cube by 3, okay. So I get xt by 3 and K2, maybe I am doing that wrong, K3. Let's calculate K3. So K3 xt equal to, you have 0 to 1 k xt and K2 xs and ks t ds, and so it will be 0 to 1 kxs is what? This is xs and this is s t. So x t s square ds only. So I have x t s cube by 3, but one more 3 is there, so 3 square, sorry, s cube by, maybe s cube by 3, 0 to 1, 3 square. Okay, so what I will keep on getting this, and I will get this, and then what you have is this series k1 xt plus lambda k2 xt, because one lambda I have taken out, plus lambda square k3 xt. This I have to see that what is this sum. So there will one lambda will also come there, okay, and so you will have finally, so okay, one lambda, and I don't know how one gets this 2, maybe there is something misprint, and so lambda by 3 you will have that coming to the power that, okay. Just check with how, I'm not sure about the 2 there. So what you have is this one. So this will let's see that 2 is there, or I have some doubt. So here what this will sum up to 1 plus lambda x over if 2 is there, 1 minus lambda by 3. This will sum up to that, and you see that what you have here, this is provided lambda by 3 is or lambda is less than 3. Okay, this series will converge only for that. And so what this method only captures us this solution, and you see that for lambda equal to 3 you will see that there is no solution exists. Okay, for non-zero, because f is non-zero, so you will see that only homogeneous equation may have some solution there. For non-homogeneous one, for lambda equal to 3, there no solution will exist. Okay, and for lambda greater than for it's a complex mod lambda greater than 3, this method does not capture that solution, but you can see that for lambda greater than 3 this is valid form, right, and you put it in the equation, you will see that it satisfies the equation. So for lambda not equal to 3 you have a solution, but only this series method captures only the half part, okay, mod lambda less than 3. So that is a limitation of this method, but at least for a small lambda you have a unique solution there. Now
how do you say that lambda equal to 3 gives a solution here?
no, it doesn't. For lambda equal to 3 there is no solution. Yeah, because you will see for put lambda equal to 3 and then see that it does not satisfy the equation. Okay,
This one does not work.
this won't because it captures. You can show that you get something absurd thing for which substitute lambda equal to 3, and for see, because it's a non-homogeneous equation, you know that see, when you have in the linear algebra also identity minus lambda this, see, or here lambda I, this lambda is coming in integral equation all.
Not clear from this, you have to do something.
You have to do something. You substitute lambda equal to 3 and look at this and put it in, plug it in the equation, you get something left side something else and right hand side something else. Okay, so that you have to separately look at. So lambda equal to 3 no solution exists because of the non-homogeneity here, non-homogeneous term here. If this is 0, then of course you may have a solution and then there will be infinitely many solutions. Okay, like in linear algebra you have lambda I minus a, if this matrix A determinant is 0, then that lambda is an eigenvalue. Okay, and then you see that this lambda x minus a x equal to 0, for that one we will have a non-zero solution. So it's something similar to that. If this one is not there, let's say 0, then for lambda equal to 3 you will have a solution and there will be infinitely many solutions. Since it's a non-homogeneous, there will not be a solution. And you see that when do we have non-homogeneous ones? There is you see that the Fredholm alternative you have to use there, the orthogonality condition.
So I'll the solution, the conditions which you have obtained, they are the sufficient condition, not necessary.
Not necessary, yeah, exactly, yeah. Okay, so that part, just I have some doubt about that one too, how it comes. So that's one, and so here that L2, this theory is only valid in L2. We proved the unique solution in L2. Outside L2, you can't ensure that, and there is one example like that. So if you consider this phi x minus 0 to x, y to the power x minus y, phi y dy equal to 0. Okay. So here, okay, yeah. So it's a Volterra equation, homogeneous Volterra equation, and here you can check that phi x equal to x to the power x minus 1 is a solution of this. Just put it in the equation, you can see that it satisfies that equation, because let's look at that. So here, so phi x is this, you have to check that this also gives you phi x. So that is 0 to x, and then y to the power y minus 1, and then you have sorry, y to the power x minus y, and phi y is y to the power y minus 1 and y. So what you get is this comes out, and y to the power x minus 1, okay, will come out, and so you will have yeah, one integrate that and substitute it, so it gives you the same function. So you have a, this is a solution. So and phi equal to identically 0 is also solution, right? So therefore what's wrong with this? There are two solutions. So uniqueness is actually kind of in the some sense it is breaking there. So is something wrong with our theory? No. What's wrong here is actually one can show that this is not an L2 function, okay. So we'll just show that this is not an L2 function, otherwise it will contradict our whatever we just established. So let's look at this one. So here if it is an L2, so what's this norm? It's 0 to 1 mod phi x square dx, and so this is anyway non-negative, so put it there. So mod, you don't need to put 2x minus 2 dx. This is because this is larger, the x is less than 1, so 2x will be less than 2, and so it's in the denominator, so it's actually improper integral. So this is limit epsilon tends to 0, epsilon to 1, x to the power 2x minus 2 dx, okay. I will show that this actually becomes infinity, and therefore this is not an L2 function. So let's see that. So let's put x equal to 1 over y, okay. So then it is limit epsilon tending to 0, 1 over y means this will become 1 over epsilon, and 1 remains 1, and 1 over y to the power 2 over y minus 2, and here you will get a minus sign because of that 1 over y square minus y square. So the dy over y square, okay. So this minus 2, this you can remove then this y square with this one, so you get that, okay. And so 1 over epsilon tending to 0 means 1 over epsilon tending to infinity. So you can rewrite it like this, that putting 1 over epsilon equal to r, so that is then adjusting this minus sign, so limit r tending to infinity, and you have 1 to r and 1 over y to the power 2 over y and dy, okay, and that will be greater than equal to limit r tending to infinity 4 to r of 1 over y to the power 2 over y dy, okay. So for y greater than 4, this 2 over y will be less than 1, okay. 1 over y is less than 1, so a smaller power will be larger, and so this is greater than equal to limit r tending to infinity 4 to r over dy over y. So that is limit r tending to infinity ln of r minus ln of 4, and so that goes to infinity, okay. So it is not an L2 function, so we are kind of safe there.
No. I think more fundamental reason for not getting it applied to those functions lies in the consideration of Hilbert spaces.
Yeah, Hilbert space, exactly, yeah, yeah.
Which L2 is there, but
yeah,
other non-L2s are not there.
yeah. So is it? Should I stop or? Huh? Okay, okay. So maybe I'll do one more result. Let's just.
It's up to 11.
Yeah. Okay. Okay. I'll do that.
15 minutes maybe.
Yeah. Now, as I wanted to do that for extending it to L2 kernels, because here we used the boundedness continuity. So, we want to get rid of that continuity thing. So, now we will assume that this little L, this k little k is in L2 0 1 cross 0 1. Okay, then so again we want to show that for some large power of t it will be a contraction. So, here we need certain notations. So, our equation is that phi of x minus or equal to f x plus lambda 0 to x k x t phi t and this k is in L2. So, we now define these a square x as 0 to x mod k x y square dy and b square y as y to 1 k x y square dx. Okay. And then you see that second integral of this will be because of this condition will be bounded. So, those integral 0 to 1 of a square x will simply give you 0 to 1 here. So, that is bounded by norm little k square. Okay, I am not writing L2 and all that, it is understood. Similarly, this 0 to 1 b square y dy is also bounded by norm little k, this little k, okay, square. So, these are some number, let us say m, you can write a squares of that m, you do not need to write k square everywhere. And then we have another notation that rho of x equal to 0 to x rather than 0 to 1, that a square y dy. And then you have by that rho of 1 is less than equal to m, the same m there. Okay. So, with this we look at t to the power n again. So, our t to the power n of phi is f plus lambda a f plus so on plus lambda to the power n minus 1 for n f plus lambda k minus 1 lambda n k n phi. Okay. So, that is our t. Now, we look at these as before, we look at the estimates of the kernels. So, here we will have this. So, what is k 2 then? K 2 x y is y to x k x z k z y dz. Okay. So, mod of this or square, yeah. So, you take a square and so this will be mod of the mod of this square less than equal to. Okay. And then applying the Cauchy-Schwarz, you have this y to x mod k x z square dz and then mod y to x k z y square dz, right. And then you can in some you can go like y to 1 and in this you can go 0 to x. So, you will have this thing will be less than equal to a square x b square y. Okay. like in the first one, if you put this one 0 to is less than equal to 0 to x, that will be a square x, right. And here this one x you replace by 1, and so that will be b square. So first on K2 we have this. Now on general K we want to show the following estimate. General Kn. So let's look at K3 and then go to the general one. So K3 xy will then be so this square will be less than equal to y2 x mod k xz square dz, and then y2 x mod k2 z y dz square. Okay, and then you have, I think, yeah, that's okay, the square root will disappear. Okay, so now again you have to see that. So for K2 we use that a square x will be replaced by z and b square y, and here you will have, then again you have a square x b square y, and then y2 x a square z dz. This you write it as 0 to x minus 0 to y. So this you can write it as rho of x minus rho of y. So we get the pattern now, which we will show by induction. So general Kn, or yeah, general Kn, we want to show this is a square x b square y and rho of x minus rho of y to the power n minus 2 over n minus 2 factorial for n greater than equal to 2. Okay, first few I have already shown, and assume this, and then go to Kn plus 1. Okay, so when you take Kn plus 1, so you have Kn plus 1 xy square is less than equal to y2 x kxz square dx, and then and then okay, so square root applying after that Cauchy swap dz, and then you have y2 x mod k z y square d k n dz. Okay, so putting that here, and here what you will have is that a square z there. So a square z, and this you have this term there. So rho of z minus rho of y. This you will take out. So rho of x minus rho of y, you will put some u, let's say, and then that you get rho of z prime. But rho of z prime is nothing but a square z. So it's you will get then finally the 1 power raised upon that. So that proves the this estimate. Okay. Now you look at Tn and show that it's a contraction for some n, and we are done. So now look at this Tn of phi 1 minus Tn of phi 2, and this at x square. So it will be less than equal to mod of this 0 to x k n of xy, and then phi 1 y minus phi 2 y. Phi 1 y minus phi 2 y dy square. Okay, and again applying the Cauchy-Schwarz, or we don't need to, I think, yeah, Cauchy-Schwarz you apply. So you have 0 to x kn, then will be bounded by this a square x b square y over n minus 2 factorial, and then rho x minus rho y to the power n minus 2, and okay, and dy, and then you have this term norm phi 1 minus phi 2 square. Okay, so here okay, a square, so here you can take rho of rho y, you can drop, and you can take rho 1, and you have factorial, this thing will come out, and you have this a square x and rho of 1, rho of x, y you drop, so rho of x to the power n minus 2 over n minus 2 factorial, and this integral of, sorry, this integral 0 to x b square y dy, this you can write 0 to 1 then finally, 0 to 1, and then you have phi 1 minus phi 2 square. Now you integrate it once more with respect to x, and now you can take this rho 1 over factorial n minus 1, you can do it here itself in rho 1. So you will have this a square x dx, that is bounded by that m there, and so some bounded quantity m here, or m1 here upon factorial n minus 2, and this is also, so you will have that one more m there, let's say. So you have m square there, and m square over factorial n minus 2, I think it's square, is, it doesn't matter whether it's square or not. So it's a large quantity anyway. So you have this control over this term, okay, overall, something like some m1 over this n minus 2 factorial there. I think it should be square of that, because we had taken square, it should be n minus 1, some mistakes here in calculation, n minus 2 square, because we have taken that square of that, right. So after that, taking a square root, you will be left with this, okay, some m square is m1 or m1 square, you can write m1. So after taking that integral over that, you get some m square over factorial n minus 2 square, take the square root. So you have finally that norm of Tn phi 1 minus Tn phi 2 is less than equal to m over n minus 2 factorial there, and norm phi 1 minus phi 2. So it's a contraction for large n, and we have a unique fixed point. So I will stop here. Okay.
Thank you very much, sir, for your nice lecture. Of course, I miss this part.
But you know
Because
all
I'm
those
busy
things.
in other issues. So if you have any query and question, you is here till now, sir? Maybe 1 or something?
Up to 1:30.
1:30 he is still here.
But you can send me an email
yes,
anytime. I'll be reply.
But this is
I'll
another
reply.
advantage because physically he is present
Yeah,
here, so
yeah.
one to one, this is more important.
No, yeah, that's
this.
always
So if there is no question, maybe during the tea or that, maybe I'll see my students Ananta, you can discuss with sir.
So thank you very
So,
much for
thanks,
your
man,
patience
again,
hearing.
and I request our chairman, sir, Professor Shahid Ali sir,
Okay,
just present
okay.
all token of appreciation.
Actually, I have meeting of academic council just now.
Okay, okay. Yeah, please, please. Thank you so much. Thank you. Thank you. Okay. How are you?
I'm just good.
Yeah, yeah, please.
Sir, one just maybe. Okay. Thank you. Because you were not there during the closing, so
I
that's
see.
why.
Okay, okay.
So it's now break for tea for 20 minutes, and after the tea, we have next speaker of the day, Professor Chaudhary. and disappearance combine. So he is very much of course service. So today anyway he is going to speak on best proximity point results and developments and some recent result in this direction. So I welcome Professor Chaudhary to deliver his talk on this particular research area of the fixed point theory.
Thank you very much. Wow. Good morning, everybody. Let me begin by extending my heartiest thanks to the organizers for their invitation, in particular to Professor Javed Ali, who personally extended the invitation to me. And I hope that all of you have enjoyed the previous lectures, all of which were related to fixed point. Now, the point is that the name suggests that something different from fixed point, which is the best proximity point. And if you are not really acquainted with this phrase, then a very natural question will come to your mind that this is a workshop for fixed point theory, and how can a topic, a proximity point be intruding into it, unless it is related to fixed point. We will see that really it is a concept which is an extension of fixed point, and we will see in particular what are the possible applications, and also what are the possible scopes and motivations behind this development. And again, you can note that developments and applications, I must admit that this is a misnomer. Why? Because in order to catch the developments and applications in a comprehensive way in one lecture is too ambitious a plan. So, what I will do is that I will give the basic ideas, touch upon the ideas, then upon the detailed technicalities, because there are two reasons for that. Because if we go for technicalities, then we will not be able to touch over different areas of development. And the second is that the technical part is related to fixed point methodology, insofar as I will give a treatment to this subject here. There is another direction and another side of the coin in the whole process. I will not go into that. And so, by this time, even if some one of you did not have that much acquaintance with fixed point theory, must have now gained some idea, some I should say some expertise, I should say, in dealing with fixed point methodologies which are applicable. So, let me, it's not moving. This is not moving. Oh, right. So, let me first gratefully acknowledge all the works which form a part of this particular document. Now, what is the program of best proximity? You can see that we have, I think from here it will be better. I was told that it will respond in a better way. Yes, from here the apparatus is actually here. So, what is the basic program? The basic program, as you can see, is the finding the distance between two given sets. So, be sure that we are speaking of distance. So, our implicit assumption is that there must be a concept of distance in the space in which we are going to work. And so, especially when you are dealing with topological spaces where there is not an explicit distance told out, the discussion does not make sense. Most generally, we will work with metric spaces, and at least with spaces where there is some sense of distance. That is not really a metric distance, but maybe a generalized matrix distance or like that. So, what is the distance? It is very simple thing that this is the distance. How do you define it? Take x out of A and y out of B, make an infimum of them, then you can be sure that this is DAB. Now, the point is that by taking the infimum, you do not commit yourself that there are actually 2 points between which the distance is actually the minimum distance, because infimum may not be attained. So, you cannot say that these 2 points, if I can find, I will have a distance. No, you cannot say. And that is the concept of best proximity pair. What is a best proximity pair? If you are fortunate enough, I tell you, if you are fortunate enough, because this is not automatic, that there is one point x and the other is the one point y star, such that dx star y star is equal to distance of AB, then we say that this is the best proximity pair. Then our two questions will come up. How to find them if they exist at all? They may not exist, the infimum may not be attained. And second thing is that in the present context, how they are related to fixed point theory. These are the two immediate questions. Before going into any technical discussion, we must give a framework in which we are going to discuss the whole thing, and for which these two questions must be answered. So, there are many ways of doing it. The way we will adopt here, before that you can see that if it is a set A and if it is a set B, two parallel lines say. So, best proximity pairs can be an infinite in number. X star y star is a best proximity point. You can see P star Q star is also a best proximity point. So, there is nothing to assume to the effect that whenever such best proximity pairs are in existence, they are going to be unique. So, uniqueness, even if they exist, uniqueness is not automatic. This is a very simple consideration which shows you. But actual consideration in mathematics arises in those spaces where you lose the contact of visuality. What you are doing is something with a subset of 2 dimensions. At best you can have a construction in 3 dimensions. But do you have a construction of more than 3 dimensions? And sometimes dimensions do speak. What is true in R4 is miserably not true, rather which is true in R3 is miserably not true in R4, and vice versa. And the second thing is that you do not have the concept of dimension in many spaces, and actually in metric spaces we do not ask for dimensions, and we are having a general discussion on that. So, things are not so obvious in abstract spaces. Now come, how can we have that? Can the non-self maps help in any way? Suppose A is a set and B is a set, and ideally we assume that they are separated, that is, there is no meeting point of them. So, we consider T from A to B a self map. So, T from A to B is a self map, and if it so happens that there is a point x star which under T is being mapped to T x star with this particular things happening simultaneously, that d x star y star then becomes infimum of DAB, A belonging to A, B belonging to B, which is precisely the distance between two sets. Then we say that this point is a best proximity point of the function T, with the help of which, or by which I must say, that the minimum distance between two sets A and B is attained, and it solves your problem. Now, question is that whether such a mapping can be constructed, and if constructed, how? And the second thing is that if we are given an arbitrary mapping, is it possible to ask and answer the question that whether such a mapping will, such a point will be there which serves this purpose? Now look at it. If you have one point z from here and the other point tz from here under the mapping T, then you can see that ztz is greater than equal to dab, obviously because this is the minimum distance. And so when you have that thing, the problem is to minimize ztz. But in minimization, there is no guarantee that it will be minimized to yield such a point x star such that this is going to happen. If in the process of minimization, you can assure by imposing some sufficient conditions that the other thing is going to happen, then you can say that we have attained a best proximity point in this particular case. Sure. So, it gives you an idea that essentially this is an optimization problem. Not only that, it is not local in nature, it is going to be global optimization problem, because you will have to minimize it over all z belonging to the domain, and this makes it into a global optimization problem. Don't be just misguided, I say misguided by the deceptive simplicity of this particular picture, because these sets may be abstractly very, very complicated in appropriate spaces, and the problem becomes really non-trivial. How it is related to fixed point? Yes. This we have spoken, and it should be, the problem should be distinguished from best approximation results. I will come to it, because there is a famous theorem due to Kaifan, and Kaifan's theorem, if we look into the early literature of the best proximity point, this is not very early because it was initiated in the middle of, I believe it is in 2006 in one paper by Eldred Biramani, and possibly also authored by Kirk at the same time. It was the first result. Anyway, I will come to it. So, how it is related to fixed point? Look at it. Now, suppose DAB is equal to 0 here. What happens? That this point x star becomes a T x star. And when you separate out A to B, then the fixed point vanishes, resembling the bifurcation in, if you are associated with dynamical systems, it is like that almost, but at least in concept. So, in that case, you can see that it is this one is a special case for that. And so, you can see the whole scheme which we are wanting to address can be thought of as an extension of the idea of fixed points. And so fixed point methodology will apply, definitely with some modifications. And this is the relation of fixed point with best proximity point. That is, we can understand it, we can view it. This is one view, but there is other side of the coin, that is the optimization side of the coin. We are not going into it because I am trying to confine my discussion only with that which is related to fixed points only. Then you can see that it is an extension of the idea of fixed point. Whenever DAB is equal to 0, then X star is becoming TX star. And so essentially, as you can realize, that these are actually the situations which are of interest. If it boils down to this one, then we will be doing what we are doing with fixed point, and there is no very speciality in it. There is no point in dealing with it separately as a best proximity point. So our interest will be in this situation, which is characterized by the fact that DA intersection AB is not equal to phi. And so now I say that what actually we do in fixed point, we find a solution of this equation in a fixed point problem. Just x is equal to tx, and then we solve it. If we have a solution, then x star is equal to tx star is that. But if you consider this equation in this context, x is equal to tx, will it have any meaning? Apparently no, but in another sense, yes. It will have a meaning in this sense that we have no exact solution of it. But we can think of an approximate solution even if the exact solution is not there. And this is common in mathematics. This is common when you are going to deal with in mathematical physics in several problems. You can see it. So we adopt that view. That is, we want the approximate solution. Not only that, we want the optimal approximate solution. What is the condition of optimality here? That this approximate solution must be tallying with this one, distance of AB. So the problem is to find optimal approximate solution of a fixed point equation. It is the problem. Now you have a fixed point equation, then there are many methods of approaching for making out the optimal approximate solutions. You can approach with those methods, but we will take a different course now. We will see that we'll combine it with this approach, how a non-self mapping can help us in this respect. Before going into that, I must give you that the Chi-Fan's best approximation theorem, it is like this one. You can say that y belongs to C, and this is actually, we won't discuss in a very, that is, time will not permit, and also scope is not there that way. So this is Brouwer's theorem, and you can see that best approximation theorem is an extension of that. And this Chi-Fan's approximation result, best approximation result, it is known that it shaped the future development of mathematical approximation theory in a fantastic way. Now, if you look into the early literature of best proximity points, then you will almost invariably find in the introduction portion that authors are writing to explicate or to alleviate the doubt that it is not an approximation, best approximation result. What is the crux of the of this sensation, it is that Chi-Pfundt's result is not an optimality result, which is the case with proximity point. And it was not Kirk, it was Eldred and Biromani in 2006 Journal of Mathematical Analysis and Applications made the first appearance of the best proximity point of an operator. Now, when everyone knows that Chi-Pfundt's best approximation theorem that I told, that it had a very overwhelming effect on the future development of approximation theory. Should we expect that our best proximity result is also having that much of influence in the future development process of mathematics also in this field? Incidentally not. It cannot be taken as that much fundamental with this one, but nevertheless, we should recognize it with proper respect in its the proper position, because these results are also very important. And now, in last couple of years, we will see that the best proximity results have been applied in a very nice way to yield some I should say to yield some applications which were not known previously. We'll come to that later. So these are something. This is, as you can see, A0 and B0 are the 2 sets. These will be very important for us. What is A0? That is, for you take x and you take A, and then dxy is equal to distance of AB. I will go to the board, and you must all agree that nothing is more comfortable than a piece of chalk and a duster for the mathematics people. So this is like this one. This is A and this is B. If you look into it, well, if it is this border is A0 and this border is B0. And then if you have a point here, then you have a corresponding point here. So it is, you can tally with it that this is A0 and B0. Again, I maintain that just trying to visualize this may be dangerous. We should have something, the better we understand, we will understand this situation, the better we have the abstract visualization of the whole thing, just cutting us away from the just geometric visualization. It's my personal opinion, obviously, but definitely the way we geometrically or just or just pictorially visualize the thing is most important. I also recognize that, otherwise I would not have just drawn this picture actually. So this is the definition that how this is the actually from 2006, the original paper. That is T from A union B to A union B is a mapping. The first part is called the cyclic mapping. TA maps to B and TB maps to A. That means A is mapped to B and B is mapped back to A. If it is the case, then we call it a cyclic mapping. It can be extended, as you can see. In literature, you will find p-cyclic mappings. That means A1 is mapped to A2, then A2 is mapped to A3, and AN is mapped back to A1. In this way, we have a p-cyclic mapping. And then this is the inequality. You can see that 0 less than k less than 1, it is there, and you can see when distance of AB is vanishing, then it is, this part is no more there, and so this is nothing but Banach contraction. Essentially, it is some kind of extension of Banach contraction suited to the context.
Due to beta money and
Yes, that was there. This was the beginning of the whole thing. And then the construction is like this: xn plus 1 is equal to txn, then dxn txn tends to distance of AB. That is some point to be noted here. Suppose this one is one set and this one is the other set. So we begin with x0, then x1 is equal to tx0. We go here and then go back to x2 is equal to tx1 and then to x3, that is tx2. So what you have here, you generate x2n here and you generate x twice n plus 1 here. If we assume that inequality, then proceed, then this is just what we do with just slight modification of what we do traditionally in the proofs of Banach contraction, the same thing. You will attain this result. So x twice n in this way will go to certain point and x twice n plus 1 in this way will go to certain point in the limit. It is wrong to say that they will go to certain point in the limit. The main thing is that this one will be satisfied. If they are, we can assure that in the limit they are going to some point, that is they are converging, then you can say that finally we have that when xn tends to x star and txn is equal to xn plus 1 tends to tx star. Sure. So this will come up. And this is, so the most important part is that to ensure when x twice n will converge. And that is not always easy. If x twice n has a convergent subsequence, then to the point to which it will converge is x, in which case x is equal to tx is equal to distance of AB. This is proved there actually. This will prove, you can prove it with no effort in fact. But when it will converge, this is the great point. There is no automatic mechanism in metric space which will ensure you that this is going to converge. You will have to make very special arrangements. If you want to have something, if you want to work on Banach space, then or Hilbert space, then you have the developed tool of Banach space geometry in your hand. You can apply it and come out with flying colors. This is one of the results. If A and B are non-analytic closed subsets of a nonlinear space and finite one span of A or span of B is finite dimensional, then this will happen. But if you say that a span is not finite dimensional, give you an example, this one. You can say this one is this, and B is this one, that is EI is this one, infinite dimensional space. Now you can readily see that the proximity point will not be there, but neither A nor B is finite dimensional. If you go to then, but uniform convexity of the Banach space will give you leverage. If you are working in the context of uniform convexity, then this is automatic, that you will have the required convergence to give you this result. So in Banach space, and particularly in Hilbert space, this will be automatic. So what was there in that, and what we have used? Just the ideas of the geometry. That is most important. And so you look back again. Let us look back. We are using here, not really here. Yes. This is, what is this? This one is a Banach contraction here, and an extension of Banach contraction in the sense that we are talking of here. So now, more than 100 years have passed since this Banach contraction was first given. And if it will not be, I will not deviate from truth if I say that hundreds of generalizations of Banach's contraction have come up. Can we use these contractions, or at least some of these contractions, for this particular purpose? Why not? I will show you one result. So let me give you one particular. This is a particular function, empty function. It is given like this one. I will not really elaborate over it because it limits supremum of something and etc. etc. This is the requirement of it. If you are if you have some interest or have some study of fixed point theory, you will be knowing what empty function is. Now, how empty function is used and what is its relevance? You can see that we are going for the multi-valued one. What is the distance between two sets? The distance between two sets can be understood in very different ways. So one of the established ways of looking into the thing is to use Hausdorff distance, that is HAB. Think of this one. What is that? If I want to see it in this way, again a picture which I discouraged, and then you take this distance and take this distance. So this distance you take alpha and you take distance beta. You take maximum of alpha and beta. This is the distance between two sets. Assume that they are closed and bounded. And now, if you juxtapose it, just A equal to B, that is, you are just putting A over B. Then what happens? These two things will just shrink to 0. Then what will be coming up? For A equal to B, this HAB is going to be equal to 0. And it is if and only if condition. Insofar as you are maintaining it as closed and bounded or at least compact. And HA is equal to, by symmetry of the definition, HB is equal to HA. And again, you can see that, yes, triangular inequality will also hold. You will have to be analytical to see that triangular inequality will hold for this particular definition. So this is the concept of Hausdorff distance. With this at hand, we have a nice generalization by Nadler of this theorem of Banach. And this is actually through this result that the study of contraction mapping enters into the domain of set-valued analysis. This is a very famous and very influential result. And after, you can see that HAB, if you treated them as singleton sets, this is nothing but the Banach contraction. Then you can have another generalization of it. That is, if you have mu is equal to this one, don't put just a multiplicative constant here, but replace it with a function which is of this character, the empty function, whose character is just this one. Then amazingly this has a fixed point. Oh, you must, I must define, which I have not defined, that yes, this is x is equal to t, x is a fixed point, no doubt about it. But if you have a multi-valued mapping, then what happens? It is taken not to a point, but now Tx is a set. In that case, we have an extension of this idea to the multi-valued case when x is belongs to Tx. You must be knowing through these lectures. It is a duplication on my part, I suppose. Anyway, now this is a part of a long, I should say, effort for generalization of Banach's contraction. Now, when you have a Banach's contraction like this, d Tx Ty is less than equal to k into dxy. So this is a constant. Next question comes. This is a logical question to be asked historically. That is, can I replace the constant k by another function? If k is equal to 1, then everyone knows it becomes a non-expansive type of mapping, and it's not easy to find a fixed point of that under ordinary conditions. There are volumes written on fixed points of non-expansive mappings, and you will need to have very special conditions in order to ensure that such fixed conditions is there. By its own merit, it is itself a subject of mathematics, the fixed point theory of non-expansive expansions. Am I correct? That is, so another direction is that y constant, why not a function of dxy? First response came from Boyd and Wong. They gave one function, putting it in place of k will be giving you the fixed point. And now, can we, yes?
Why it is the function of dxy? Because dxy is also a number. Why it cannot be a function of x and y?
Actually, k is a number. We are wanting finally to have a number, but that context of group. So these are the applications even which could be derived. So next comes the p property. Now, what we were discussing is a bit restrictive. What is the restriction? That we were doing with this type of situation, that here is A and here is B, T is mapping from A to B, and then whole B is mapped into A. This is B, and B is also mapped into A. So this is like going cyclic. Is it possible? In our original way of thinking, we did not assume that cyclicity of the mappings are necessary types of things. We started with these types of non-self mappings down there. And what is then, the methodology should be changed now. What is the change in methodology? That is, again, borrowing in some ad hoc manner the property which is called this P property. As you can see, that when y1 is equal to z1, y2 is equal to z2, then this is the property. Then this is y1, z1, this is one proximity pair suppose, and y2 is equal to Z2. This is naturally A0 and B0 of the whole space. This is A and supposedly this is B. If it so happens these two are both are equal to DAB, then these two lengths are equal. This is called the P property. It has weaker versions in the literature. I will not go into that much of details. And when weak property, P property is satisfied closed interval AB? This is one. AB are non-empty bounded closed and convex subsets of a uniformly convex Banach space X. It is automatically satisfied. And second thing, another example is this is the modified P property or like that. So as you can see, when you are going to use this P property, then what is automatically satisfied in a uniformly convex Banach space or in Hilbert space, you are just borrowing in an, I should say, the borrowing of idea, not the borrowing of the technicalities in one sense, but in an ad hoc manner from those structures into your metric space, because you need to borrow, because in your metric space you have nothing, no structure. Only when you come to the cat spaces or like that, then you have the comparison triangles or like that, you can take up what you see actually into those spaces. That is a separate study, I will come to that. So with this P property assumed, then you can have results again on this. You can see this is one way, multi-valued. I have taken multi-valued, you can as a simple case take it as a single valued. So this is Adler in 2000, I believe, in 2012 it is. And as you can see that the subject has not completed its two decades of existence. So there is a, this is an example for that. And this is multi-valued non-expansive. It also has certain, on Banach space, if you impose certain conditions, then it will also give you the best proximity point. I have omitted, then there are also in 2022 a nice result has been published, and which has applications again to homotopy types of things. And this is again, I have repeated. Let us go back this way, and this is the result. I think I should, how much time I am having now? 20 minutes. 12:45, fine, 25 minutes, 25 minutes, 25 minutes, okay. So this is common best proximity point. This is again another problem. When we speak of fixed points, then a topic very naturally comes, what is the common fixed point? So why not talk about common best proximity point? Can there be results on best proximity point? Yes, there can also be results in this way. This is common best proximity point result. As you can see, these results are also available in literature. Now comes that you see, I think Professor Imdad will be speaking in the next session. So, and he is going to be relational fixed point theory. So, we will, myself will also be in the audience, because it is the expertise of Professor Imdad that he has done quite a commendable job for the fixed point community. The main idea is that if we are looking into the traditional proofs of Banach contraction mapping theorem, dTxty is equal to less than equal to k into dxy. We assume it for all xy. There is no need to assume it for all xy, because in your, if you look into the traditional proofs of that, then you begin with x0, then tx0 is equal to x1 T x1 is equal to x2, what you do is do it on this particular sequence, which is actually called the orbit of x0 to be formal. And now in the whole process you need to mainly you need to apply this inequality only on the sequence, on one sequence which is obtained in this way. The other parts are not that much required. So you can just avoid those things. You can just make them redundant and just maintain that yes, my inequality needs to be satisfied only on certain subsets of x cross x. What is a subset of x cross x? R is a subset of x cross x. Whenever xy is belonging to R, then I say that these or these other types of inequalities, not necessarily this one, is satisfied, maybe my condition, and this is the, I should search for a minimality of the R so that it is sufficient for me to give you the final result. Still, R sometimes will require a structure. What can be the structure? R is, like you can see, this is a relation. What can be the structure? One structure analytic. We can blend them and see that the results are obtained. And actually results are actually obtained, you can see. So I skip the details of that. So sometimes we call it a G proximity point. It was the result published in 2023, quite recent result. And as someone was asking me in the time of in between, that what can be the directions which can be taken up. So this is one direction in which proximity point theorems have not advanced in a very large way. One can take up and combine it with the metric space by imposing some additional structure, see how these results, new results can be obtained. And now, these are the results I will definitely, and this is the one that is the measure of non-compactness. It also just plays a very large role in the whole process, and Professor Javid has proved certain results on proximity point using measure of non-compactness. These are the results. I should skip the details and should maintain that with Caputo derivative, the fractional differential equation they have considered under certain conditions, it has been proved that it has an optimal solution under certain conditions. I have not given the solutions. It is a very interesting application. Why interesting application? The application is interesting because the solution, sometimes what we do, sometimes we seek a solution, there exists a solution or like that, of some differential or integral systems are like that. This is a very, as we have learned from Professor Bohuguna's lecture, that this is a very, I should say, very interesting and very useful method of mathematics, particularly of applied mathematics. And now the thing is that there may be certain systems which does not admit of, or there is no guarantee that it will admit of solution. Then what should we do? We should go for the optimal solution. Optimal in what sense? There is no definite benchmark. We need to define optimal according to our needs. Your need for doing that thing, what you need for optimality may not be coinciding with me. So this is something optimal with respect to what? This is a very great question, and you will have to set the problem in that way and then obtain the result. And this is one of the examples in which it has been done, and I think this approach will be, I do not say this is this technical approach, I say it is the approach. The approach of idea may be very useful in different areas. I will touch upon this one. This application is in chaos solitons fractals. This is some Altun and etc. in 2021 they have published. Now, what we know is that fractal. What is a fractal? Everyone knows what is a fractal, and mathematically if you want to see it, then fractals are self-similar sets. That means there are many fractals. One of the very most common fractal is your Cantor set. That means these are the types. You can repeat this process. This is not a fractal in the mathematical sense. This is a fractal which you can, after certain iterations, you can have this figure, but if you go on doing it, then in the limit you have certain sets which are called fractals in the mathematical sense. And arguing in the mathematical way and in the way the argument is taken in computational science, rather particularly in computer science, are not one and the same. You will see in papers of computer science these are called fractals, but if from mathematics one question comes that where is the limit? You have done 50, 500, 5 crore, 50 crore iterations, but you have ultimately stopped. Where is the limit? So the limit is always, this is the basic difference in the two approaches. That is, xn tends to x. This means mathematically very certain. Xn is equal to yn for all n. This means that the two sequences are one and the same. But from the computational point of view, this means xn is equal to yn insofar this can be asserted. That means it depends on your power of computation. So these two approaches, if not contradictory, are not one and the same. So anyway, with that at hand, let us look into it. So there is a self-similarity. In a very restrictive sense you can do that. If you want to see the self-similarity in it, you will have to commit yourself to the group with finite generators if you want to be mathematical. But if you can, in some limiting process, push it to a transformation group with infinite generations, then only in the mathematical sense you have a self-similar type of thing which can be described as a as a fractal. Anyway, for our purpose, this is the Hutchinson-Barnsley operator. That is, we have contractions, and now we do not require them to be contractions. These may be generalizations of the contractions even. And then you have this operator Fa union from 1 to n Fai. Ais are collected from Kax, that is, these are compact sets. So the place of abode for fractals are compact sets. This is not my terminology. I am borrowing it from some very highly cited paper that this is the place of abode for the fractals. And if you look into this equation and see that there is a point C when Fc is equal to C, what happens? Just forget something in between. Everything is changing with Fi, but when you are applying F on A, the intermediate things are not visible. Got my point? I think that I have a circle like this. This is F1, it rotates, F2 it rotates, F3 rotates in the reverse direction by pi, 3 pi, and then 2 plus 1 pi, anyway, whatever be it. But if I look into the circle, just disinterested with a disinterest in the fact that what has happened with the particular Fis, then I will see that the circle has not changed. I will see that there is a self-similarity in the whole thing if my viewing is through F. This is actually the crux of the Hutchinson-Barnsley theory, and in this way this is a very famous theory for generating fractals, HB theory, and has many applications actually. Now the point is that if we can, we have the, and for that purpose we call it, this is called, I have not written it, anyway it is written later. We have an extension of it. Yes. Let me give you the result. Now, everyone, it is known that, let me again go to the board, H is the Hausdorff, let me use the small h, it has been used as small h. Small h is the Hausdorff distance. Now, A and B are two compact sets. In this way, if we begin with XD as a metric space, then K is the set of all compact sets and H is the Hausdorff metric, then this is also a complete metric space whenever XD is a metric space, a standard result. And now, from that construction you can see F is a mapping from Kx to Kx. Instead of Kx, if I take A and if I M and if I take N, these are subsets of Kx. Mind it, very important to note that elements of M are compact sets. Elements of M are compact sets. So, distance between M and N, what is that? Should be the Hausdorff terms of Hausdorff distance, that is minimum or infimum of HAB. A belongs to Ka and B belongs to Kb. We call it here, for notational purposes, let us forget the previous notations, HAB. We call it. I mean, subset, we are taking subsets, not that, sorry for that. So, we call it is equal to HMN. If we construct this one as the function f as this one, such that this one is satisfied, then we have a unique best proximity attractor. It is a generalization of the previous theorem. Here we deal with what is called iterated function systems. This is called iterated function system known as IFS, very special name and very famous name. Then here we will have PIFS, that is proximal iterated function system. What does it generate? If we go into the numerical study, this is, you see that this is R. That means 1/8 radius, with 1/8 radius you take a circle. This one is this. And you have F1 this one and F2 is this one. With this you construct the PIFS, and what is the fractal generated? You can, as I told you, that this is the approach of the computer science. You will have to stop somewhere. But in the whole process you can see that yes, some pattern is being generated. This is the two-dimensional Cantor set, as you can see. If you suppress one dimension, you can see the 1/3 Cantor set is coming up. Just suppress the two dimension into one, your familiar Cantor set. Two-dimensional Cantor set is generated, and this is generated by PIFS, a very separate way of generation from the previous one. This is a marked improvement. I cannot give you the details of the, because it requires a little more elaborate discussion, but this is a marked improvement. And as you can see, it appeared only in 2021, and you can see that it has been further, in furtherance of it, some results have come, not too many results yet. This is another direction in which the young researchers can proceed with the proximity point theorems. I was being asked by several of the young researchers, so I am telling this particular point very specially. My time, Javid will not allow me more time, I know. Just, I will not.
7 minutes, 8 minutes.
Okay. So I will be, that is the coupled fixed point. What is a coupled fixed point? You can see fx is equal to, fxy is equal to x, fyx is equal to y. This had a controversy actually, and some coupled fixed points it was given that these are nothing new, only the fixed points on product spaces or like that, but there was also a counter argument for that. So viewing something from another point of view does not nullify the first point of view. This is also the fact. Anyway, so we are not going into that, but beyond this thing, because this controversy will not just touch us if we are going to have the contraction like this one. This was the famous work of Bhaskar, 2006 again. Yes. So this is the actually the, and we could, this is the coupling actually, coupled best proximity point, and it is the coupling. What it is the coupling, I will give you the idea. This coupling has been utilized in working out the generation of fractals already. You can find the paper, I think 2022 or like that, in chaos-solitons fractals. You can find the paper. And coupling has also been utilized in other contexts as well. So this is like this one, that you have AB, from here you take x, and from here you take y. So you make fxy, it will plunge you here. And if you take fyx, then it will just move you here. So this is the coupling, that one is coupling and it is moving it, the product of the whole space is moved to one space, and the other way is also there. In this way, we can have also, what is the gain in it? As you can see, that we require these two equations to be satisfied. And this is one way of attaining DAB. And you can see this is other way of attaining DAB, because neither x is y nor fxy is equal to fyx. This is the difference. These are the two different pairs. And by a single theorem or by a single algorithm, you can just derive or have in your hands two pairs which serve your purpose simultaneously. This is the importance of coupling, and it is possible. We can give you the result how. This is an example for the result. This was in 2018. This is, as you can see, by mimicking the result of Eldred and Biromani, this could be done for the coupling, and that too for multivalued coupling. But we have used delta distance, not h, in this particular case. So I should not proceed any further, but I will give you some. Already we have mentioned that fractal generation by proximity IFS, proximal IFS, is a good candidate for taking up research. Then construction of algorithms for proximity points. You can see that we have many, in fact, it is called the constructive fixed point theory, that we have different algorithms, fixed point iteration sometimes called, that is starting with Mann iteration, that is one step, then Ishikawa iteration, three-step iteration, Noor iteration, etc. Many types of iterations we have. What is the utility of it? Because whenever, in many cases you see that we prove that such an integral equation has a solution. How do I prove it? We quote some, if we are going to utilize the fixed point theorems, then we quote some fixed point theorem and then satisfy it in the context of our integral or differential equation, and then conclude that it is satisfied, so it must be having a solution. So, the question that it requires to find a fixed point is bypassed. Just a fixed point is there is sufficient for us. No, this is not the case. I will give you just one example. Suppose we are doing with, everyone knows if we have a 3-dimensional sphere, suppose, and in this 3-dimensional sphere, let it be filled with water or any fluid, whatever be it, and then T from 3-dimensional sphere D3 to D3 filled with water, a particular continuous function. And from Bauer's theorem, what we have? There is a point z is equal to Tz. Got it? It's very well known fact. But how do I realize it here? If you go to fluid dynamics, tell some, that is applied physicist or applied mechanics people, just construct such a table which realizes this one. What they will do is that they will make the arrangement of a pipe this way, that is, fluid is taken out and infused. Got it? And how do you know that this is a continuous transformation? Very simple. Go to the fluid dynamics equations. It is a perfect fluid, then solve the Bernoulli's equation. If it is a viscous fluid, then go for Navier-Stokes equation. It will give you a continuous path, and then the capillary flow, and then just squeeze it. It will give you, and again, no experiment on earth is ever perfect reflecting the mathematical idea, not even in the atomic and subatomic domains. There is a gap. Here also, you cannot make a pipe into a line. This is fact, but you can make it approximately to the desired degree of approximation, insofar as it will not contradict the Heisenberg's uncertainty principle, whatever be it. So, it is infused from here to here, and here is the point z is carried to Tz. This point is z1 sucked out and placed here to Tz1. So, there is a strong topsy-turvy of the fluid. This is called the turbulence of the fluid, a very technical name. If you are a student of fluid dynamics, you know that this phenomenon is called a turbulence. It's a chaotic phenomenon. And in the whole process, there will be a point z bar is equal to Tz bar. If you are here, you will be just thrown out here. But if you are at z bar, then you are safe. But you are safe only when you know z bar. And that is the reason that you need to know z bar. And that is the reason that you need to construct algorithms and iterations, whatever you say, which takes you to z bar. That is the justification of that from the applied point of view. And now this also applies to, if you justify it for fixed points, why don't you justify it for the extended concept of proximity points? There is an interesting whole thing in it. Now, proximity points involve two sets. Although subset of a same set, they can have very different characters. If you are doing with one Banach space, then yn plus 1 is equal to xn alpha n xn plus 1 minus alpha n, then t xn, it makes sense. But here it may not make sense. They can have very, very different characters. So their construction is not going to be very easy. And this is very interesting type of problem which has a very vast domain of unexplored vast domain, I say. And so this can be taken up. And lastly, I must say that one is that the proximity point problem in cat spaces. Here, what are cat spaces? That this is, the time is very scanty, that it is that there are comparison triangles, and with the help of that we have we invite geometry into that space. So geometry of the reals R3, R4 or like that. Now professor has done a very good work which has come to our notice, that you have taken the comparison triangles in LP space in one of your works. And we really appreciated this work, and we felt that it is going to just give us an opportunity to work in more general setting. And so here also the proximity point can be studied, and I think if you particularly in Carpathian Journal of Mathematics in 2024, one particular paper has already been there, and so it can be taken up for consideration. And lastly, I must say about one thing, that random version of proximity point studies. Why we require randomness? Suppose some of you have definitely read Shakespeare, and particularly the Macbeth, it's not Macbeth, it's Hamlet. There, Hamlet affected madness, and some person, they were commenting like that, there are methods in its madness. So if you look into the sky, just look into how the the clouds just conglomerate and then they disperse, they scatter around. You will see that nature is exhibiting madness, but there are methods in this madness. And whenever there are methods, there are regularities which can be caught in the language of mathematics. And what we do is that we have the mathematics to deal with random phenomena. We require for our, in addition to our differential equations, we require a random element infused in the differential equation. So it becomes a random differential equation. And again, in this random differential equation, when you are going to solve the differential equation or give at least the existence of solutions by using fixed points, for that random part what you will do. And random differential equation is not a very recent development. This was, I believe, in 1972, A.T. Barucharid. It was his work, random integral equation, all the same as differential equation. And again, Segal and Barucharid, their famous work on random fixed point. So you require a random version of these fixed points. And when you require a random version of the fixed point, then why not go for random version of the proximity points? This is also a good problem and will serve many of your purposes. There is another point, which I will end, that for the purpose of uncertainty coming out of the random nature of things underlying, there is another way of doing, that is the stochastic way. Sometimes random and stochastic, I have seen papers written as stochastic fixed point theory dealing with random fixed points. But when you go into the stochastic differential equation, the story is very different. You don't use these types of integrals. You have Ito's integral, Stratonovich integral, you have martingale and etc., all types of things. And in that domain also, the fixed point study is there and important, and also in that domain, I believe, although I feel that not much has been done, I have not come across any such paper, at least now, but I believe that in that domain, stochastic proximity point problems can also be taken up with, and it is mathematically profitable, I believe, that these things can be done successfully, and I think will be giving good leverage in our theory and applications both ways. So let me end here, and these are our, as I promised you that I have not gone very deeply into the technical studies, because technical studies are quite elaborate. It would have restricted what I wanted to say, but I dwelled upon the ideas only.
So, any doubt, any question you can ask Professor
I
Vinay?
want you to go back to the fractals.
The fractals, right? Yes.
Just close to that.
Close to that one, yes. Close to. Yes. This one is the fractal generation. Back.
Regular fractals.
Regular fractals, yes. This one.
No, these are.
No, this is proximal. This is.
Forward. Forward.
Next
Forward.
Yes.
Here we go. So I want to make a comment here. I believe I talked about it in the course. This business is very late. So the original definition, which is the contour set, as well as this one here, the Cox curve, they were created for something very topological
Yes.
and specific.
Yes.
The formulation as a fractal and as a fixed point of the famous system, this came very late in the game in the 80s.
Yes, yes.
So, for example, for the student, for the contour, it was to find a compact set which is completely disconnected.
Yes.
And this one, that's why I wanted to, it's one of my favorites. And this one is very interesting. It has a very beautiful formula, which is, when I ask my calculus students, can you draw any continuous function? And the answer is, for the student, yes. And of course they are wrong, because the moment you put your finger with a piece of chalk and you move it,
yes,
then you have a problem because you are differentiable.
Yes.
And this one was interesting about it. When you go to infinity, it's really interesting. If you take 2 points on the boundary, 2 points on the curve, the distance between, the travel distance along the curve is infinite.
It is infinite, right.
So this curve was created at the time when they were crazy. I'm talking about 1850 all the way to 1910, 1915.
Yes.
They were crazy into coming up with mathematical objects that will answer negatively some questions that are of topological nature or analysis nature. But later on, of course, with the Banach contraction principle, then we found another way of looking at it. That's just one comment. Second comment, which in this famous book about fractals, they claim that they are natural, but they are not natural. Nothing in nature is a fractal. They say, oh, everything is a fractal, but it's not. These constructions are so artificial that in reality, what we see is not a fractal. It looks like a fractal, but it's not a fractal. It's a kind of some weird object. Yeah. And these are too fancy, too mathematically beautiful to be fractals. It's really interesting, very interesting.
Yes, and I fully agree with you on that point.
I did not hear about the other one, which is very interesting, the proximal
Yes.
fractal.
This is somewhat an extension of this one, actually. Thank you, Professor.
There is a one pick also. Next picture.
Next
slide. Next slide.
Next slide, I should go here.
2-dimensional type, sir? This one.
The Coach curve in 3 dimensions. It's okay. And you will also have in 3 dimensions that type of computer generated figures, and that, as Professor told you, that you will have to stop somewhere when doing something in computer. And there you lose the particularly non-differentiability things are like that, actually. So, true. And so you can also have the Cantor dust in 3 dimensions. These are available and we obtain. This is not something that we just simulated. These are available types of things. For illustration, I have put it here. But this is simulated actually. We have done it using Python. We have verified it and done it using Python. Although the authors in that they have given, but additionally we have verified it.
Sir, you have used one approximate compact set. N was some approximating compact. So what do you mean by approximating compact set with respect to M? It was written somewhere.
Somewhere, possibly I skipped that. So it is sometimes in.
Was in the theorem of Alton.
Let me go back.
Like three compact or something.
No. Approximately compact. I will give you.
This one, previous slide. Yes, this one. This is approximately compact with respect to M.
N is approximately compact with respect to n means then n with respect to m, n is losing, that is we are understanding it that not with full boundary. Maybe some part of the boundary is there, but not with full boundary. That is what we are going to.
So sir, a similar thing can be done for p variable, like sometimes data dependence. We do like in contraction with data dependence. We have some data for these proximal things. Is that is possible to for data dependence?
I think it is possible.
Okay.
Because data dependence.
Randomness, so that is also one
Yes,
kind of thing.
one kind of thing. But data dependence may be of two types. One is that you just give an epsilon variation to it and see its variation, and the another is that you put randomness on it and then see what is the random character of the final result. Both are important, and in the randomness ultimately we will have to go to the expectation value or like that. That way we will have to value it, otherwise not.
Sir, in one slide you used Caputo differential equation.
Caputo, it is his work. Actually, Javid.
Generalization of ordinary derivative to fractional derivative. And so we have collection of like contraction, right? Family of finite contraction. So my question is, can we have something for non-expensive as well?
No, not yet. We don't have. I don't say it is not possible, but I have not seen it anywhere. And we have also tried it with that, but we came out with negative results.
Okay.
This non-expansive types of things is something which is not so easy to handle like this one. Algorithm.
Because we need some geometry or
Many other types of things supplementing. And one thing that it should not be, I have always used those contractions which are generalizations of Banach. But starting with Kannan, there are many other contractions inequivalent to Banach. These are also applicable here, which I have just omitted.
Okay, so Professor Vinayak is here, so maybe you can discuss more during the lunch and after the lunch. And so thank you very much, sir, for your
Thank you.
on this particular part of the anomaly analysis, proximity point results. So let us again thank the speaker.
Thank you.
Now it's a break for lunch break for 1 hour. So 2 p.m. we will assemble again here, and after we have a closing ceremony.
So you got some of your answers, I think.
Yes, sir. I have read all these papers.
Okay, then very good. This is the Carpathian journal.
Yes, sir. Total. My doubt is that this maps we extend in non-expensive map. These are maps जो context define किया है सर non-expensive map पे define कर सकते हो.
I doubt. I doubt.
My brother start coupled best proximate point.
Oh, yes.
Thank you. Coupled best.
For the beginners, I can say x is a set equipped with an order and x y belong to this, then this statement, this what how they are related. Obviously, you can have this very feeling. There are two elements x y in a set x, they need not be related. They may be related, they may not be related. So, what is, if you look at here x cross x, R is a part of x cross x, R can be equal to x square, that is x cross x, and in that very situation you will get the natural results. What the result you have, if you take your relation to be universal, they will be what they will getting with the natural form of the result. This is the reason. So, I speak this, skip these things. Order and other definition is something over there I would like. So, here two elements are related about order, preceding, succeeding, all these business I hope that you know. Now, here you have another definition the same way. What is there? Ordered set, then an element. This is what is called as upper bound or lower bound, and then supremum and infimum. This all you know, because this we have already done in the real analysis. There I am also realizing that need not to be explained. Like if there is a set, there is an order, all those kinds of notions which you use in early mathematics, upper bound, lower bound, greatest lower bound, least upper bound, all these facts are there. These are stated in these definitions. Now, next is what here an ordered is called, this is the complete lattice here, definition 1.4, this is also there, sometimes we are using that an ordered set is said to be a complete lattice if every subset of x has infimum and supremum. This is the definition our student used to study at lower level in our MSc classes. Now, and here now the first thing is look at the order preserving. You have x and y are related, and how about t x t y? This is something which should be noted. Like here, if you take x and y are related, how about the image t x t y? They may not be related. So, this definition restricts that x and y is related. This definition says that their images are also related, and this is essential because this is the fact we will be utilizing in the construction of the definition, how you have the sequence of the traits. Now, next thing next definition is this is what about the metric spaces here, because since we are going to work with the metric space x d, on this you have an order, and then you have the completeness or other definition. So, here one thing I would like to say point out, because you all know that they are with respect to metric completion or continuity or something, all these results that we have tried to improve later. So, this is a complete, this triplet what I am saying over here. Now, instead of considering a pair, now you have a triplet x d and equal to or less, means you have a triplet whenever you call a metric space. So, this is also, now here comes that result I was quoting. This is a very famous paper, and this is often referred by the working by our youngsters utilized. I think it has very frequently cited, and here is the theorem statement. First is what, that x and t x they are related. Okay, like you take a point x naught and then corresponding image t x. Generally, what happens, they may not be related. Here, first restriction we require is what, that they are related. This is the first restriction we have, and then this is the relational contraction. It's just they call it relational contraction when x y are related. To look at this definition of the contraction is not the contraction we work. This is with respect to that order, and x d is complete, t is continuous. Here continuity of t is taken. The reason is what, that here theorems often have two facets. First is what you prove, that there is a fixed point. Thereafter, you prove whether the fixed point are unique or not. That is the reason why you have that t is continuous. Like in the case of the contraction map, t is always contraction, but not only contraction, this continuous, but it is uniformly continuous. But look at here. In our case, we cannot say. Therefore, we have taken that this is continuous. The map is continuous. This is the condition which has been imposed, and x d is complete. These two conditions are in the natural setting. Recently, we have adopted in our ordered theoretic setting that these two can be also like R completeness R continuity, they will come thereafter some time. And here is the sixth condition. This ensure you how you will get the uniqueness of the fixed point without this here. So, this condition is there to ensure the uniqueness of the fixed point. Now, as you see, still it looks very natural, conditions look very natural, though you can say nothing can be more natural like Banach contraction principle, but this is also natural in our context. Now, two fellows, Juan Nieto and Rodrigo Lopez, Juan Nieto and Rodrigo Lopez, they have utilized this result slightly some kind of modification. One case is what the map is increasing, other case is map is decreasing, and that formulation is look at here. Though T is increasing, just look at there, that was the case, both cases were open, like either they are increasing or decreasing. They choose in the first theorem, this has come to in 205. Look at that very result came in 204, this very result came in 205, where they choose to T to be an increasing map, and then you have this sequence having convergence, and here it has been added. If it is there convergence in K, then increasing sequence such that x n converges to this, then x n and x they are related. That is what is how it is taken. And again you have the same condition you have in that very case, and here you have another contraction that you call again relateless contraction, because whenever x and y are related, once he has taken the increasing, it should be taken as if x equal to or less than this. Then T has a fixed point. This was in fact Juan Nieto and Rito Lopez have two papers, one paper in order, general order, another paper is Academia Sinica, that is published English version. And now another result of the similar kind here you have, that is theorem 1.3. What is there? That only two conditions they have replaced by these two conditions here. First thing, second was replaced by second dash, that is T is continuous or x d satisfies the following property. Here if they can, x n is a decreasing sequence, because he has to do decreasing sequence here. X n is a sequence in x such that x n decreases to x, and x n equal to or greater than x. This is what is meant by there. This means they are considering decreasing sequence. Then there exists x naught such that x naught is T x naught. So, these are the two things, because here we often have equal to or less than. So, in the case of the decreasing map, they took that x naught is equal to or greater than T x naught. And then the conclusion of the previous theorem, that is another theorem we used to hold, and here in the following lines you can see under what conditions you can have the unique fixed point. With that very condition along you have over there pairs, and then global convergence of the successive approximation. Where is that? Every pair of element x has a lower bound or an upper bound. Okay. So, it was slightly light under the condition they take every pair of elements of x has a lower bound or upper bound. So, this was at another theorem Nieto and Lopez, and here the third theorem. This came again into now here is another theorem which came in 207, and the theorem is as follows. Here you just look at this, that complete ordered metric space x d tau T is monotone, means it includes both the cases, unifies, and T is a continuous map, this such that it satisfies the following properties. There is a sequence x n converges to x, where consecutive terms are comparable. Then there exists a subsequence, obviously x n k, such that this is comparable to x, and comparable here sometime is we have used the utilize big bracket x n x, and that amounts to say either x n equal to or less than x, or x n is equal to or greater than x. So, he was a and then again you have the last part, and you have that. So, just look at the difference is very little, like sometime he used to take increasing condition, decreasing condition, and very slight improvements are there. Now, and in all the cases we have not said the order we have considered is partial order. It is not mentioned over here, but in all papers right now from beginning our order is partial order. Partial order means reflexive, antisymmetric and transitive. So, the relation which enjoys these three properties in all these papers, this is there. Now, when our journey over here is very accidental, we were working sometime here and there, and we are not daring as if such thing is possible. In fact, here there is a very recent paper at that very time, that was Hashim bin al-Mashayikh. Hashim bin al-Mashayikh removed rest of the two conditions, that is reflexivity and antisymmetry, just using the transitive property. He was able to extend this theorem, these two theorems. Like here the partial order, the improvement was this, that the relation they consider is, our ordering is partial ordering. Here that is not mentioned because in the paper it is not mentioned, that is why the typist has not included that this is a partial, in fact this is partial ordering. Now Hashim bin al-Mashayikh, what he did, he has relaxed two conditions, that is reflexivity and antisymmetry in the partial ordering, and then he was able to prove this very result in the same way, and his paper appears I think 16. Now here what we are trying to do over here, we started working whether this very result is possible for a arbitrary relation or not. So, I was just in the company, Dr. Aftab, which is very much over here, was trying this thing, that whether this result can be proved for an arbitrary order or not, means like this very ordering which you consider. Yes, this is the result. Yes. So, here we are able to relax this very condition like ordered property up to the extent of arbitrary relation, that amorph by relation, and later we realize that this condition is very tight. While proving also we are finding difficulties, but after it was through and we were happy that the proof is okay, because I talked to Aftab that you have to be very careful about the proof. I was also very fine because the condition is very tight, it is not be, maybe we are having somewhere committing a mistake, but that is not the case. But finally the proof was okay, and then after that we submitted this paper to a journal, initially to the proceedings, but it was not forwarded as the case may be, and then we have submitted our paper to fixed Journal of Fixed Point Theory and Application. So, this is so this is the theorem we were established this. Here our operation, our relation R is a binary relation. It does not have all three properties. The improvement accomplished is very little. That is what, that conditions of reflexivity, antisymmetry and transitivity all got relaxed, and here we have in the same condition, that just look at this R complete and R complete. Okay, one more thing. After this we attempted to relax the condition. There is another paper we have written, that refinements through the relational contraction principle, where we have included this relational version for these conditions like R complete and R continuity, and it is suitably defined because all previous theorem they were all natural, like XD or relation R or whatever is said, that is natural setting. Natural setting means they all refer to XD with the topology of D, that what is discussed. Now here in that very paper we are able to relax and have that very formulation. So, R complete means completeness, means a relation R which are related, means terms are related as you have maybe or ordered sequence, their limits are there and their Cauchy sequence converges, that is the definition. And same thing used in the continuity, that T xn converges to x, this implies T xn converges to x. The sequence is what those relational sequences means either increasing or decreasing, that the case may be, and x n x either x is equal to or less than x n is equal to or less than x, or x n equal to or greater than x, that is the case both cases. And here you have another thing, that in the for the fixed point you are working here, the problem that T x is R s connected, that previously you do not have such definition. Just look at this here, T x is R s connected now for the uniqueness part, and T is R here R preserving contraction, and here T our sequence is R preserving sequence, whatever is the order that is preserved. So, we are referring to the constraints of preservance, that is the case. अब इसका प्रूफ आप जो है वो चंद लाइनें देख सकते हैं, कोई बहुत मुश्किल नहीं है. Look at here, by the first condition we are able to have the sequence of iterates, you are master, x naught is related to T x naught, and by T closeness we have defined as that T closed, like x y belonging to x, this is a heavy condition, then T x T y belonging to R. So, x y belonging to R, this is the condition we have utilized, this is a tough condition, as you can say in the Banach contraction principle, everything is very natural, but the conditions of contractivity and completeness is very strong, very stringent, but the fruit is wonderful, but the conditions are very strong here too, that T is closed means x y belonging to R, we refer that T x T y belonging to R, that is the condition we have used. So, x T naught x is equal to or less than T x, now using that is what x T x naught belonging to R, and then by using the T closeness you can have this sequence constructed, that is here this sequence, and now this is going to belong to R by the T closeness of this, and thus what you have in our notational case that x n plus 1 belong to the relation R. Now, up to here everything is okay, just by recursively operating our definition you have come over here like this, and by our definition that is what called relational contraction, this is equal to or less than that, and operately n times as you do in every case. Here is you have the using the triangular inequality, and then this, and then up to this, and this is replaced by a infinite series, this by infinite series, and then this is equal to or less than this, which tends to 0 as m tends to infinity, and this gives you that this Cauchy sequence is Cauchy, and then you have the limit up to here, and by continuity you have the fixed point. By using the continuity here, continuous R, then x n plus 1, this converges to T x, at the same time this limit could be x, and by uniqueness of the limit this could be T x, that is the case. So, you have T x is s, this is the same thing as we have in all standard books in MST, that is what you can call that x is a fixed point of T. Up now what you see over here, if R is D self closed, here you have taken the definition D self closed, look at this, x n is R.
So, x is the limit of x n, okay.
Uh-huh.
Are they belong to R, x n belong to R.
Yeah.
Limit and x n are comparable means belong to R or not.
Ms. Majani, what is the problem?
How is like this? So, x n goes to x.
Yes.
Is it?
Yeah, this both cases, two cases, either this or this. This they have denoted in the paper.
Or not.
Yeah, yeah. No, this is if you take increasing. Yeah, yeah.
Continuity is not needed. This
Ah,
continuity is not needed.
yeah. Which condition?
That R continuity is not needed. Which is R contraction, not needed.
But that is I got your point. You are right. That is the consequence. As you know, here he missed the point that every contraction map is a continuous map. Similarly, every R contraction map is a R contraction. Right, agreed with you. This here, thank you. You are correct. Now, what you see there is sequence x n k, x belongs to R for all k belonging to n naught. On using assumption, you have this very thing here starting. Here x n k, you put the value here, this is there, everything is okay. Here x n plus 1 turns to here. Now, that was the case here. The other part is what, that is the uniqueness of the fixed point. This is slightly new, as you have made the effort that we have taken is what, that our path, it is path connected not in that sense we have in topological spaces, that in topological spaces we define path is a map from a closed interval to the topological space. That is not the case here. Here path means a discrete path between 2 points. You have a finite sequence which you can join them, these 2 points, like taking one initial, another final, and you join this just by x, y. Now you have a sequence, suppose this is z naught and this is z k, this you take as b or x, but I take a b because then you have a sequence here that is equal to or less than z 1, equal to or less than z 2, equal to or less than z k, such that z 1 here these sequences z I, z k I running from anywhere, these are we call as order preserving sequences. So, the order is preserved, that is the case. So, here we have utilized that very definition as if the to prove the uniqueness, here you start from here, and T x inductively you have T n x is equal to x, T n y is equal to y, and these 2 points belong to x, and therefore, here we are using R x connectedness. There exists a point z 1 z 2, a sequence, finite sequence z 1 z 2 z k, such that this is the initial point and that is the final point, and here these sequences are order preserving, that is z I plus 1 belongs to R for each I. Now, as R is T closed, by using proposition 2 we have this belongs to this, and for each n belonging to n naught, you have here d x y, and you have put this thing d to the power T n x z naught T n z k, and now you utilize those points that z 0 to z k just by putting over here this inequality here. We are using triangular inequality, and you got from here up to here this thing, because we are inserting the points here like to the power n z naught and then z 1, then z 2, and then finally z k, and from here you have this thing, and you apply time and again our contraction conditions, alpha times this, again alpha times this here, and then alpha times this, and this you have this thing. So, here I is equal to 0 to k minus 1, this thing which tends to 0 as n tends to infinity, okay, and getting us that the fixed point is unique. This condition was slightly different as the case may be. Now, what happens here are the consequences which you have, that in our case under the universal relation R is equal to x square theorem 2.2 reduces to the classical Banach contraction principle, because if you look at the conditions they all got subsumes, and you have the classical Banach contraction principle. Setting R the partial order theorem 2.2, we obtain theorem 2.1, 2.2, 2.3 of Nito and Rodriguez-Lopez. Assumption B, T close is equivalent to increasing property of T. That is what is said here. So, this is T property, this is just an observation, and next theorem is what? The setting R is equal to or less than this, the dual relation associated with the partial order, this in theorem 2.1, we obtain theorem 2.4 and 2.5 of Nito, Lopez. Clearly, assumption B, what that T is closed is equivalent to the increasing property. That is trivially there. You have this is increasing property. Okay, theorem 1 of like the observation 4, particularizing R by pre-order in theorem 2.1, we obtain the theorem 1 of Tunisi. Here transitive relation we get, as I mentioned earlier in the beginning, that the motivation for our work was this paper of Hashim bin al-Mashayikh, that was 2.2 and 2.4, and we were able to attempt this so as to improve our taking care of transitive property of this. And here you have finally a indirect kind of thing, that certain paper of Tunisi and Samit, these two are most active fellows, Tunisi, I feel sorry for Tunisi, because Tunisi has done good results, but he is not able to present them properly, because initially we just look at the idea, all idea that can be largely attributed, because we are doing somehow following refinements here and there, but main content whatever was initiated, that was Tunisi. But one drawback is over here, that he is not wonderful in presenting, he is not able to write his paper properly. Otherwise, his whole idea was exploited by what Rand and Runing, and write that very beautiful paper, which is often read by everybody in the proceedings. Now here, okay. Now here is, there are 3 examples here, and I may recall my role as a supervisor to Dr. Aftab Alam. When the theorem was proved, and we were somewhat convinced that the theorem is proved, then I asked Aftab, prove that how it is different to the other theorems. Aftab was complaining to me that submit the paper. I am saying no, I will not submit unless you come out with the examples. So he worked hard for quite some time. Then he came out with 3 examples separately, so as to justify that this very result is a genuine refinement over the result of Hashim bin al-Mashayikh. And after that I submitted this paper, and when I got the revision, there was nothing in it here and there, and the referee was satisfied, fortunately for our point of view. And here is the first example. Here R is our natural setting, my binary relation is this, means x is equal to or greater than y, and this is obviously partitions the R2 x cross x into 2 sets equal to or greater than less than this one part he chooses. And then you have our map here, that is T x 4 plus 1 by 3 x. Clearly R is T closed and T is R continuous. And here you have the contraction condition, everything is okay. Now what we need to show is what fixed point. T has a unique fixed point. Here you have the RS connectedness of this. You can very easily feel that this space T x is what? T x equal to or greater than y, this T x is always there, and here we have no problem, because it is whole half plane. You can always have the finite sequences, this is there, and therefore unique fixed point because of the closeness. Now another example, here we have, this is all done by Aftab, full marks to him, because I only said no, I will not submit the paper unless you have examples. My only credit, I said no, you cannot submit the paper. Here this, the map we have considered, here is the domain you have taken 0 1, just chooses 5 elements. For the youngsters, for our seniors, they are very sharp, as Professor Dhage has pointed out a very interesting observation. Very interesting observation, thank you. Just look at here, 5 as many as 5 elements. For youngsters, if you know, if your contraction survives on these 5 points, 5 x, you are fine. Any contraction map that need to survive only as many as 5 points here in the relation they are active. Otherwise, in the other spaces, in the other part of real line, no problem happens, you don't care. Then you have here, just to look at, because of T x 0 and 2, they are not the part of 2 x, here they are the part of outside, and therefore only thing you have is what, then 0 and 1, they are the part of this, that our ordered sequence or order preserving sequence, that is only this one, 0 1 0 1 and 1 1 for all n belonging to n, which gives rise xn as a sequence which is the part of this, either these 2 elements. And 0 1 is closed, as you know, we have all these conditions are satisfied, and you may have that the contraction condition that you can very easily verify, and thus all the conditions as see in the theorem are satisfied. But look at what is the advantage here. Notice an example 2, the binary relation R is not any one of the earlier known standard binary relations. So this relation, such as reflexivity, irreflexivity, symmetry, anti-symmetry, transitivity, completeness, as well as weak completeness. So this again shows one aspect of the game, that this is a genuine improvement over the other results which have already discussed many. And now finally this result, the open interval 0 1, you have taken as your setting. This is not complete in the natural sense, as you know. Here you can find that this is R complete. So, this 0 1 is not complete, but it is R complete what is there, and oh, that is example 3. Just look at here. Example 3, the ambient metric space is incomplete, which is R complete. Just look at this first observation, that 0 1 naturally you have excluded the point 0, that is why completeness gone, but it is R complete, and underlying map is not continuous, which is R continuous. So, and underlying map is also not continuous as far as the is not continuous, which demonstrate the only existent part of theorem 2.2, but not uniqueness part. I am talking about completeness of T x, because you have seen that we are talking about T x whenever talk of the uniqueness. So, T x and T x is what 0 1, okay, that is there. So, these three theorems situationally, what is this? These three theorems situationally prove that there is an improvement. Now, I will not tell you this is very significant, very somewhat refinement. This is a refinement over all previously known results, and this came to when he started trying to extend this theorem to Bird and Wang type contraction condition. They do not survive like this condition, Bird and Wang type condition, everybody knows d of T x T y, this is equal to or less than phi of d x y. We have already literature on this, and we have also worked on this. So, here the arbitrary relation does not survive. We need an additional condition, arbitrary condition. It does not survive. Why? Because of the requirement, because we need to have our another function which we define as locally transitive, local transitivity, and thereafter we are able to prove this result. So, what I am trying to say that their improvement is little but not very significant, because we are not able to get one example so as to say genuinely this is different. That is the case. This is what I personally feel. Now, this is what we do, and there are two papers for this. You have to look two papers. One paper is Journal of Fixed Point Theory, another is in Axioms. I think Axioms, Filament, refinement to refinement. Some another, yes, no refinement, that is there. So, there are three papers in all. You can just look at this. This is the initial and very natural, very simple setting. I think anybody can do it as far as my observations are concerned. Now, we come to another part of this. How much time I have? Chaliye, let us go. Now, here we have first observation for the youngsters. I am not saying anything for my seniors. Maybe here, as soon as you take the non-expansive map, what happened to the literature? Like if you take a non-expansive map, here I will be talking, there is nothing other than Professor Muhammad Amin Khamsi. You will see here his contribution. I will just state the theorem, because maybe you feel very taxed if I go through the proof. What is very wonderful about this is what you take any sequence of iterates x n in x d, x n converges to x, okay, which is fixed point. So, any sequence of iterates, as I have said in the beginning, the conditions are very terrific, contraction and completeness, but the result is wonderful. You take a point of iterates these days, you construct a sequence limit point with a fixed point. So easy. Even if you do not know, you can very easily do it using the computers. But what will happen to this very thing, to this case? as far as non-expansive map is concerned. Non-expansive means distance cannot increase, maybe it can be equal. What happens, this result is no more there, then x need not converge to the fixed point of t, what I have taken t as, to the fixed point of t. This is a very simple example you can utilize and you can convince yourself. Just you take x is equal to, because I am taking on the metric space, x is equal to minus 1 to 1. This is you can find in many books, and you take here T x is equal to, define the map T x is equal to minus x. The sequence of iterates need not converge to the fixed point. Yes, have some idea? Any point you take which is non-zero, iterate need not converge to the fixed point. Just look at this fixed point is what? Is 0. Just look at this map, T x is equal to minus x. So, T x is equal to minus x, and fixed point is obviously 0. Here you look at the fixed point is 0, but iterate at a non-zero point, iterates for a non-zero point, does not converge to fixed point of t in general. That is what I am trying to say over here. Now, then obviously plane may not be the case, and those who are having interest here, many like Professor Khamsi's area. This is the Professor Khamsi's area where he has done a lot, contributed very significantly. Then how about the results, possibilities to prove the fixed point result? So, in this regard there were 3 papers simultaneously, one by Broder, another by Johad, and another one above all most general, that is by William Artkirk. So, William Artkirk has proved a theorem, and these 3 papers came simultaneously in 1965. So, this came simultaneously in 1965, and they are still often referred here. Now, I am having first result before you on the Hilbert space, a self map or a map mapping to a closed bounded convex subset of f h. Then here your non-spec, this is the existence theorem, then there is a fixed point x. You cannot have the construction procedure before you have the iterative processes as you have the case. So, in this regard there is a iteration scheme process, a lot of literature is there, many iteration schemes are there, but here only existent part, that there is a fixed point x such that T x is equal to x. So, just out of these 3 condition is very simple, as you know, your Hilbert space fitting is wonderful, this is very natural geometrically as well as in many ways. So, prove the theorem. So, this is the most radical result, this came in 1965, and then another result. Oh, क्या हुआ? इसको कुछ गड़बड़ हो गई सेटिंग. Yes, yes. ओहो, उल्टा यार. Yes, next. Then here first the definition is required so as to state the next result, that is uniformly convex Banach space. So, this property is well known, we used to teach at the MSc level, like we know the geometric property. What geometrically says that any 2 points joining on the ball, you take geometrically unit ball, of the case may be, the midpoint may not be on the ball, but they should be very close to the ball. That is the definition we abstract, and here you have the definition is equal to or less than, and the points are very close, is still their midpoint does not lie on the space on the ball. And our student, MSc student, they may recall their book, the case may be on x equal to R2, Siemens book, and they can very easily infer about these balls. I do not want to mention the ball here. This picture you may have in your mind. Siemens book, especially topology, this is there, and there is one more on this very figure. This is the Siemens book. Look at with the natural ball on the R2 itself, not Rn. If you can take this generalized, the natural ball with Rn with R2, they are always uniformly convex, because if you take any 2 point, the midpoint, this will be not the case with this or with this, but here if you just look at any 2 point, they are very however close the star, the midpoint definitely this will not be on the circle or on the circumference, but this will be very close to this. So, here the other examples which is indicated over here. Here with this definition like that is mentioned in this here on the Rn I have mentioned, but if you r is equal to 2, you can very well see this diagram, and these are what the balls centered at 0 0. As just look at this, like if I remember some of x plus y equal to or less than, some of the properties are what will be here, mod of x plus mod of y for equal to or less than 1, one of them is this. Here of course x y they are in the ball, and this is the natural ball, and then maximum minimum, so many things that is there. So, here some of them, what this example says that this is not a property which is of the set, this is a norm property. Same set with a different norm may be otherwise. So, R2 with the some other norms may be not uniformly convex. So, here this very theorem is what uniformly convex Banach space K, a bounded closed subset and convex subset X, then T from K to K non expansive mapping T has a fixed point. And then came here definition of non diametral points, or you can say we are looking towards our Banach spaces here a normal structure. So, two terms are involved, that is reflexivity and normal structure. So, this theorem cannot be stated, though this is the most general result what is here. So, here you have the non diametral points, the first definition 2.3, here is the definition that when a space Banach space is said to have the normal structure. So, it says what, that every closed convex subset of a Banach space with diameter equal to this has normal structure. And here you have diameter as the case supremum. So, we may start our students teaching what is the diameter. By the way, what is the diameter of a circle if you use this method? Suppose I have a circle of radius r, what will be the diameter? बोलिए, कुछ तो बोलिए. Is it the same definition or otherwise? Or the natural norm? It's natural. What do you look at? Diameter of a circle? Yeah, there can be more distance than this. समझ नहीं पा रहे. I am asking you whether this natural definition coincides this abstract definition with the natural definition. Yes, definitely yes. So, here and reflexivity, as you know, that natural embedding that is onto x to x double star. Okay, this map this is onto, or there are other ways here. There is also one more definition. So, now normal structure, here is the fixed point, the theorem 3.2 due to William R. Kirk, a great man who has written many books. The books by Gobil and Kirk you must not have forgotten. The book by Samin Khamsi and Kirk, that too is very handy these days, and many other ways he has significant contribution. Professor Kirk, here is another paper by him, and that is very significant, and this is the most general. What is there? X is a reflexive Banach space equipped with a normal structure, means whose every closed bounded convex subsets of X are having the normal structure. Then K has a normal structure, have sets. Suppose that K has a normal structure, then T from K to K is a non-expansive map, then T has a fixed point. These are 3 related papers, all came in 1965, and many things I have to say, but I do not have time here, like Hilbert space has never fixed point property. You define the right shift operator, it does not have the fixed point property, and many more. A lot of literature is there, but I do not want to go here. I want to come to the, as I have said, that without Professor Naveen Khamsi, nothing is possible. Here is the first result. Yes, here he has considered a partial Banach spaces. Okay, partial means a Banach space which is equal to the partial ordering, and we say that T from X to X is monotone, and this is what we call monotone non-expansive mapping. I have not mentioned over there. Then with X equal to R this, then T is called a monotone non-expansive map. So we define a monotone non-expansive map means the partial ordering is there, in that we consider monotone means increasing sequence of elements, and then you have this monotone mapping. Okay.
Order and norm compatibility. Is there any compatibility between norm and order?
Yeah, sure, definitely. That is true. That too is there. But here we have taken the ordered monotone. We have named the word monotone. Okay, so that is obviously cases, both the cases we have. And then Bacher and Khamsi, there is another definition. Now here you can have this increasing interval or interval in a partially ordered norm spaces. Okay, here is the order. You take an initial point P, and any element this, if such that P x belong to this or P is equal to x, then that is was the case. These were the intervals, order intervals in the partial ordered set x this, with initial point P and maybe terminal point, or you can say the end point Q. So these are the two. They are intervals. Because of the ordering, these intervals are possible in the even. Now here comes the theorem. Here again Professor Khamsi is available, as I have said in the beginning. When the Hayesh and Khamsi proved this very result, here is the result, that the partial ordered Banach spaces are there such that order intervals are convex and closed. Assume that X is uniformly convex, K be a bounded closed convex subset of X, and let T from K to K be a monotone non-expansive mapping. Then there exists this such that these two elements are comparable. So again he put this condition, very extra condition, that X naught and T x naught are related, as we have in our theorems. Without construction will not be possible. Then T has a fixed point. So this is the result by Professor Khamsi. Now what we can apply our case situation or relational consideration? What are the improvements which are possible? In these results we adopt, rather than partial ordering, we adopt the relation, our amorphous binary relation. Then these are the improvements we are able to assess here. We worked with some in teams certain points here. Partial ordering can be replaced by a transitive binary relation. Here again I have said that the condition of amorphous binary relation is very tight, but here look at this, up to transitivity we are okay. So partial ordering can be replaced by transitive binary relation. Transitivity of the relation is not needed in the whole space, but it can be limited on a suitable subset of K. So it's transitive binary relation. Transitivity of the relation is not required on the whole space X, but it can be limited to a suitable set. Closures and convexity of R interval are also not required, but it suffices that merely certain relational intervals in K are closed and convex. Furthermore, convexity and closeness of the whole space are again not needed, but this can be limited. Bounded the whole set K is replaced by relatively weaker assumption, as you see just now. What is the possible result? Here the map. This is ulta chalega kya? No. is third. I am not going to the details. These are this is required. Here this definition 3.7. Image of AX, AR. Here you take those elements in K such that AX belong to R or X equal to A. This is the definition. It is also in X, and similarly here pre-image of AR, that is the reverse order, that you can call inverse kind of situation, that is X belong to R, X A belonging to R and X equal to A. So, if you take the partial ordering on this, if you are these definitions of the real line, then this coincides our interval, which is called closed, like these intervals in the real lines. If you take R and you have this ordering, natural ordering, then these two intervals they reduces to this, as on the case of in the real line. And here is another lemma which will come to our statement. A Banach space X is reflexive, as I have said in the beginning. Every decreasing sequence K n of non-empty bounded closed and convex subsets of X have non-empty intersection. This is one of the lemmas due to Sumelian here 32, and this is not empty. This we utilize if you used to have the statement. Now, here there is a function that you can call this 3.3, this is 3.8, this is also by these authors. As you see, you define a bounded sequence x n in K, X norm space, Banach space, order partially ordered Banach space, or here in our case ordered, and then a function K from 0 to infinity. Here no need required, nothing is needed. Here tau x is equal to limit superior n tends to infinity x n minus x such that x belonging to K. So, this is what is named is what type function. So, this was named as a type function for a bounded sequence x n in a Banach space. Now, here another lemma, that is again by the same group, that is K be a non-empty closed and convex subset of a uniformly convex Banach space, and K is a map from this to this. Then type function, then T has a minimum, then T has a unique minimum point Z belonging to K such that this is the definition here, tau x, tau K. So, there is a unique Z such that tau Z is equal to this infimum, that is there. Now, here we have our results to the extent just look at it, there are three conditions. X be a uniformly convex Banach space and K a non-tree subset of X. Let R be a transitive binary relation on X, then T from K to A and R norm expansive if there exists K such that these three conditions are there. X naught T x naught belonging to R, there is again for the sake of the construction of the sequence. This set image T x and R is a non-empty closed and convex subset of convex for each n belonging to n naught, and T n x is bounded. Then these under these three conditions, that very theorem, as I have said in the beginning, that can be lightened or it can be improved up to this extent that we can utilize our binary relation here. Then she has a fixed point. Okay. So, shall I go for the proof? No. How much time I can take? Finish. Okay. Then let us see the corollary. Because now, here is another statement that if R is replaced by R inverse, we call here, though I go very quickly, RS means R union R inverse. So, here if you have the R and then you have the inverse relations, means x y belonging to R implies x y x belonging to R. So, here there is another possibility to have an analog or a kind of dual kind of result here, if there is decreasing order here, that image of T and x naught is replaced by R, and that way since x T x naught is equal to R less than x naught, you have that, and here third condition is same, then T has a fixed point. Okay. There are many, I have no time, but I wish to tell you that something more we have done here in this regard, that is asymptotically non-expansive mapping. I am stopping here. This is the result which did. This has come in 1922, I think, or 21. But recently we did a paper that is on asymptotically non-expansive mapping along with Hasanuzzaman, where you have utilized these ideas of Professor Amin Khamsi to prove a result, to prove some results which are published very recently in 2024 in Romania Journal for Fixed Point Theory, Romania. That is very recently published. We extended to the theorem of Gobil and Karp. So, that very theorem means asymptotically non-expansive, means that map is non-expansive for t to the power n, as we have the case. So, if t is we have not t non-expansive, but t to the power n is non-expansive, and that very result we have published, and we have also published some example in that very paper, because referees these days ask that how can say your paper your result is better, then we have to construct some example, then we have constructed an example. So, that was the most recent result we have done. What I can say that if you try by some work, not very hard, because all I have is stolen the ideas of Professor Khamsi. I have not contributed new ideas here, just using his ideas we are able to prove such results which are predictable. This is what I wish to thank you. Maybe I am not very good in presenting like Professor Khamsi or Professor Vinayak S. Chaudhary, but definitely I owe a lot. I wish you all the best, especially youngsters, not our senior, they are better than me. So, I wish you all young guys all the best in your future life. Okay. We can discuss sometime here. If you have something to say about this, I will discuss over here. Okay. Thank you.
Thank you very much, sir, for your nice talk in this direction, from contraction to non-expansive
Yeah,
mapping,
yeah.
and then finally monotone asymptotically non-expansive mapping. So, if you have any one or two query questions.
Most result is by latest result is that one which came in 224. Yes, sir.
I want to say something about the second part.
Which one?
Second part.
No, it's okay, it's okay. About monotone mapping.
Yeah.
I don't want people to understand that this monotone mapping is just another generalization of the Banach contraction concept. Okay? Let me give you something very important. For example, when you are looking for, remember the talk by Professor Dhage, where he looked at the differential equation, normal, he just gave you an example, where you take the differential equation with an initial condition, change it into an integral equation, and it becomes a fixed point equation. Okay. What happens if you are interested to find a positive solution? Now, when you are looking for a positive solution, you are involving the partial order. You want to look for a solution that is positive. It's no longer just looking for a solution. The techniques used by the people working in differential equations is the concept what's known as lower solution, upper solution.
Yes.
And what is the concept of lower solution, upper solution? These are functions where u and t of u, t is the integral operator, are comparable. So, to help you see the power behind what you saw, there is a book by Lakshmikantam, I have it by the way if you're interested, where he talks about this in an entire book, all of it. So this is not to be taken lightly. This has some major applications. So, and the last comment, I want to go back to this theorem that you see behind, theorem 4.2. What we discovered is that the appropriate technique to study the non-expansive mappings, monotone, are iterations. I always look, for example, I am unable to find a monotone version of Kirk's fixed point theorem, because Kirk's fixed point theorem is based on John lemma, minimal set,
Yeah.
and so on and so on.
I've read it.
But these theorems are all iterative in nature. You start with x0 comparable to t of 0, and then you start to take what? The iterations according to man iteration and so on and so forth. This theorem gave me the hardest problem, this theorem 4.2. And why? I couldn't do it with man iteration. I had to use what I called Fibonacci man iteration. I was able to do it with Fibonacci iteration, but I couldn't do it with normal iteration. It's still an open problem and mystery to me. There are some very interesting open questions for people who are interested. Thank you.
It's okay. Thank you. In fact, what we did, since you did for partially ordered, then we feel that we can just more limit this. That's the case. And in the proof, maybe what you are saying is 100% correct.
You said equal lower solution as well as upper solution.
Yes.
We don't require we require only one.
Yes,
either
yes,
either
yes,
lower.
yes,
I have
of
put
course.
something.
Of course, of course. No, I meant the concept of.
Concept.
I didn't mean that you need to
Yeah,
assume
yeah.
both.
Usually
No.
He's just a general idea.
No,
What is the
some
basic
people
philosophy?
either, but why? Because in the theorems that Professor Imdad was mentioning, there exists an x0 such that x0 and t of x0 are comparable.
Yeah, sure,
so
sure,
x0
sure.
can be less,
Very
it can
true.
be bigger. Yeah.
Very true, very true.
Nice.
Yes. Its consequences sometimes that there is dire. But since you adopted this, we feel that let's do it. Maybe what you say finally, because difficult questions are not easily answered, as you see that the case may be. This is a kind of trivial shift, as the case may be, because you have operator, then R operator, and R monotone. So similarly, we consider R monotone. How long it will be fruitful, that is still to be seen. Yes, thank you very much. Any one of you? Okay.
Thank you very much, sir, for
Thank you.
your talk.
नहीं बजे इधर बढ़ जाते हैं बढ़ी ओह ये
एक डाइसिंग चार्ज को देना, एक स्पीकर को लगाना आपका।
ये भी रिकॉर्ड करना है।
तो सर से पूछो, तो दोनों लगा देना, फिर जो डाइस पे रहेगा उन पर लगाना।
Then we can start closing program. एक आध वर्ड खड़े होकर नहीं बोल देना, ओवरऑल थैंक्स तो वही बोलेंगे। आप तो यूनिवर्सिटी बिहार लोकल कोऑर्डिनेटर है ना पूरा, आप थोड़ा सा कुछ भी थोड़ा बहुत कुछ बोलना है, थैंक्स बस यही करेंगे। ठीक है, वो इतने नाम हैं। Okay. Good afternoon to all. Welcome to this closing ceremony of GIAN course on fixed point problem, the old and new. So, for this session, just I invite guest to the dais. Of course, there is no proper dais, we have just simply. So, I invite Professor Amin. So, please have a chair with us. Maybe in center. Yeah, because we need a basically center. You remember? Yeah. That's Chebyshev Center. We need some Chebyshev Center. Yes, maybe somewhere. Okay. Professor Shahid Ali Saab, Chairperson, Department of Mathematics. Please, sir. Professor Mohammad Saeed Saab. No, big boss is here, so just please, because he's an advisor of my advisor, so he's one of the senior person in this series. So please, sir, have a seat. And Professor Viva Sharma, ma'am, local GIAN coordinator from university. Please have a seat. इधर रखो ना इल्मा एक और नाम क्या था MS खान साहब मेरे पास है BC शाहिद अली साहब इंदा साहब 6 कहाँ होंगे अभी 5 ही तो होंगे मुझे में लगता है चलिए मैं चौधरी साहब को इमदाद सर हो चुके ऑलरेडी हाँ मैं okay I invite Professor Chaudhary Sahab just to have a seat because he did not join on the first day because he arrived just yesterday sorry easily so please let us okay so now I hand over the program to our MSc student Ilma so maybe she will conduct the program from now.
I would like to start the program by giving a tribute to the founder of this prestigious institute, Sir Syed Ahmad Khan, by saying, "होगा किसी फलक पे वो खुर्शीद जलवागर, कहते हैं आफ्ताब कभी डूबता नहीं," which simply means that on some other horizon that sun is shining, they say the sun never sets. Respected Professor Mohammad Amin Khamsi sir, our Honorable Chairman of the Department, Professor Shahid Ali, Professor B.S. Chaudhary sir, Professor Mohammad Imdad, Professor Vibha Sharma and Dr. Javed Ali, and of course Professor MS Khan, and all of the delegatories and professors who are present over here, my seniors and my dear fellows. Assalamu alaikum and a very good evening to you all. I welcome you all at the closing ceremony of this GIAN program. So yeah, we are at the very near end of this program. This 5-day program has provided us with a lot, more than what we can expect or more than what we have expected. So at this very moment, I would like to congratulate each one of us, all the professors, teachers, students, for this very successful completion of this GIAN program, which is possible only because of our very enthusiastic and a very positive participation. So once again, I congratulate you all, and not wasting much of the time, I would like to call upon the course coordinator of this GIAN program, Dr. Javed Ali, to present a report of this program. Before that, sir, I would just like to mention something. I would like to thank you, sir, on the behalf of each one of us, not only for organizing this program, but also to encourage a participation in it. You know, we all are well aware that a program of this dimension cannot be organized overnight. You know, the wheel starts rolling months in advance, and that's what Javed sir is doing now, not for days, but for months now. So on that note, I would like to invite Dr. Javed Ali to present a report on this program. Please, sir. Welcome, Javed sir, please.
Thank you, Ilma. So now we are going to just towards the completion of this program after a long 5 days. So just I want to share some brief report of this program for last 5 days. So first of all, we receive 127 application for this program across the India, from south to north and east to west, even from Kashmir to even Kanyakumari. We have a one participant from Kanyakumari. Okay, and after scrutiny process and all the things, I shortlisted or just selected 62 participants for this program, and all of the basically participants attend this course. And of course, so we have very wonderful discussions and lectures during 5 days. So our main speaker from Professor Amin from Texas, University of Texas, El Paso campus. He delivered almost 10 hours lecture in last 5 days. And of course, I listen. Of course, it's a second time for me. He is a very wonderful teacher. Of course, he is a very deep researcher, but on the same time, he is a very wonderful teacher. So, of course, all participants know about this fact from now. And our other speaker, Professor Dhirendra Bahugna from IIT Kanpur, he also delivered the basically 2 lectures. Basically, just he left in this afternoon because he has some engagement at his home. So he speak about the basically one lecture was on the fixed point theorem and then application to the differential equation part. Our another resource person was Professor Muhammad Imdad. So just he delivered a very expert talk in the area of relation fixed point theory. So he started the basically problem from relation contraction to the relation non-expansive mappings. And then we have a very eminent researcher Professor Bapu Rao Sidhage from Maharashtra, and really his talk was very wonderful and it was very informative. Generally students appreciate your talk very much, sir, because it was a very fundamental in start. Of course, after that you have so many deep results and this one, so we couldn't spare more time for you, but hopefully in the whenever we have another opportunity in future, we will invite you again. Okay, and we have another eminent speaker, Professor Binayak S. Chaudhary from Indian Institute of Engineering Science and Technology, Sipur Habla. So he also discussed the very nice important branch of fixed point theory, of course, important extension proximity point results and their extensions to different directions and some interesting application in this work. And I also just recall some of my colleagues, they helped us and conducted the basically tutorial classes. My colleague Dr. Asif Khan, he engaged the student and conducted a tutorial on the MATLAB, and Dr. Fahim Ali was also in that tutorial. So basically Asif focus on the MATLAB part and Dr. Fahim just discussed the some fixed point iteration and their simulation process to the participants. And another tutorial was conducted by Dr. Aftab Alam. So basically he gave the glimpse of the important and significant generalization of the contraction principles. So we were basically organized these tutorials during the last 5 days. And of course, as a part of culture, we organized a one university visit for 3 hours on the second day, and it was very wonderful. So we visited the library, especially the museum part, that is very rare because it's not open to all every time. So we have to take the appointment and this one, but our librarian allowed, and we visited the very nice rare collections there, and then Sir Syed Academy or museum, and finally we visited the last part, that is Victoria Gate and Strachi Hall and Jama Masjid area. This was very wonderful. So this was the basically journey. So of course, Professor Amin discussed a lot of nice results. Of course, from the, because title has the two one part is the old, another is new, and time was not so much enough, so he could not go enough in the new part. So if we have a opportunity again, I am requesting to Professor Vibha ma'am, because she is the GIAN local coordinator. So, maybe we can plan again for the basically another part, that is new part, because we have lot of opportunity in this part. So, we could not cover the basically this part, new part. So, maybe in future we will again submit a proposal for the second part, and even all the participants want this one. Am I right? Yeah. So, so I think we can. Yes, yes. So maybe I will request to Professor Amin. So maybe we can make a proposal to the next part. So anyway, so this is a brief report, academic report, of course, on this GIAN program, and I am very thankful to all participants and resource person. Of course, official vote of thanks will be delivered by the Viva ma'am, because she is the overall means local coordinator of GIAN program for the entire university. I am just very course coordinator. So thank you very much, and just keep in touch. And now you have a interaction, you have lot of discussion with the among the participants, with the experts. So continue this spirit and try to learn things. Important thing is not mathematics, because during these interaction we also learn lot of things, means secrets, hide secrets we don't know even. He discussed those secrets. Discussions means between the Eckland and Keresti and Kerr and lot of things, because he works with those peoples, so he know very well. So this is very important. So with these words, I think thank you again. So please, Ilma.
Thank you so much, sir, for sharing your views and the report of the program. Now let's moving on towards the memento presentation. First of all, I would like to invite Dr. Zishan to present a memento to Dr. Fahim Ali. Zishan sir and Fahim sir, please come on over here.
कोई और ले लेगा फोटो.
Now I request Dr. Majumdar sir to please come and present the memento to Dr. Aftab Alam.
This is just a small token of appreciation to our tutorial and this one.
Now I request Professor Aslam Siddiqui to present a memento to Dr. Asif Khan. Please, sir.
Aslam bhai, yes. Asif, this.
Now I request our chairman, sir, Professor Shahid Ali, to present a memento to Professor B.S. Chaudhary. Now I request Javed sir to provide the memento to Professor Amin Khamsi, sir.
Amin. Thank you very much.
Now I would request B.S. Chaudhary, sir, to present the memento to B.S. Dhage, sir.
Sir. Easily, sir. Easy.
Now I request Imdad sir to please present the memento to Professor Vibha Sharma. sir, please stay here for a moment. And now I would like to request Shahid sir to present a memento to Imdad sir.
Thank you, sir.
Now lastly, I want Amin sir to present a memento to Javed sir.
Sorry. Just reflex me. No profit. No. Mine is there. Okay. Thank you very much. Please. सर सही सर ठीक है कुछ अपना कुछ जो भी शेयर करना हाँ स्टार्ट
Now I really request all the delegatories who are present on this panel to come over here and share their views about the
maybe
program.
from here
Sir, I request you to come first to share the views.
just यहीं से बोल दिया खड़े हो वहाँ पे वो नहीं माइक चाहिए
तो दिया नहीं दिया अभी नहीं दिया
सही से लगे मोमेंटो
Although I am not sick in the lecture, but
concepts
I have attended 2 lectures of Professor Hamsi Ami,
बस ये हो जाता है
and it seems to me that he is not only a good discussion, but he is a very good as a teacher. He is very good. He is an excellent
नहीं
teacher.
इनका कंप्लीट
I have listened only
उनका
to
मतलब नहीं तो अपनी थैंक्स
and moreover, I especially again thank to Professor Hamsi because he is staying here at medical for a long time and he has some problem with medical problem with him, and even then he delivered a series of lectures here. And moreover, I also thankful to the participants who have come from the different corner of West India, and hopefully hope that you have enjoyed the lectures given by different speakers. Very nice lecture. So with this, thank you all.
Now I would like to invite Mohammad Amin Khamsi sir to please come and share his views.
First of all, I would like to thank everyone, starting with the students. Our essence, our existence depends on you. You are the spirit that keeps us alive. And let me just tell you that when Javid and Izhar contacted me to come and do a GIAN course, I did not respond for quite some time till Izhar started beating on me and he said, answer the emails. Okay, fine. I answered the email. Now I am inviting them to apply for the second one. They are not inviting me to come. No, I'm inviting them to apply for the second one. And the reason is because I feel some incompleteness. Profoundly, I feel incompleteness to give you the big picture. And the reason why I want to give you the big picture is to make you, as I told you yesterday afternoon, that I want you to be the best. Not only to do fixed point theory, but to do something that will put you on the map, that will make you known, that will make you respected. So the second part, if we go there, will raise the standards from the old to the new, but new that is people struggling with, and you will be working on stuff that will make you something. So let's hope that we will be able to have another one, okay? Thank you. Thank you very much.
Now I would request B.S. Chaudhary sir to please share his views.
Thank you. So very good afternoon to all of you. everyone in the dais and in front of me. I was here only for one day, but the impression I had and the trust I developed, the trust on the young researchers, the trust developed through their sincerity, through their eagerness. I had only one lecture, that too on a subject related to fixed point theory, no doubt, but I had been very hasty. Still, because I had to cover many things actually for giving an overview, still many of these young researchers approached me, and that is, I am proud that this community of researchers will one day come forward with that much of intellectual valor and make India proud. And it's great to hear from Professor Khamshi. Also, although I did not have this opportunity this time to attend his lectures, that as now the proposal is going that he will be coming for the second time, then it will be my pleasure to participate in it as an attendee and hear to his lectures. I especially my special thanks to Professor Javid for his kind invitation to me, and wish you all a very good, prosperous academic life ahead. Thank you.
I thank everybody on the panel for their generous views.
आप बोलिए यही
क्या बोलूँ रेगुलर पार्टिसिपेंट्स आप ही हैं As a whole, I enjoyed the program, this GIAN. I was here on my leave because I am now a retired person. But I remember that when I came back from my PhD from Australia in topological groups, Imdad and 2-3 more people were without any supervisor. Then I asked them to start in this area. So starting from various construction principle and their generalization. And I see now my son, my grandson, and many grandsons over here. So I really enjoyed my visit here and hope that all these new people will take the importance of their lectures, but always start with a simple thing. You can't reach the level of Professor him or him. So don't think that what is happening here. Start with small things, slowly and slowly and slowly. And then, inshallah, one day you will have good papers, do result like Professor Imdad, and then. So I wish you all your luck with your future program. Okay? Sir, your health is very good and you are very active, so maybe in future you may see more grandsons.
I thank everybody on the panel for their views. Before moving on, I would like MS Khan sir to please present a memento to the chairman of our department, Professor Shahid Ali. Sir.
Before the end of the ceremony, I would love to see the grandfather. Take a picture, you know.
Now the focus is on you guys, all the participants. I would. Before moving on to the participants, I would request Imdad sir to please come upon here and share your views on what is all about the GIAN program.
I've already said a lot in the beginning. Finally, I just want to say whatever I wanted to say. That I wanted to read a couplet again, but that is all exclusively meant for my younger generation. As I have said that day for my younger generation, today I will also say for my younger generation. रंग लाती है ना पत्थर पे घिस जाने के बाद, रंग लाती है ना पत्थर पे घिस जाने के बाद, सुरखरू होता है इंसान ठोकरें खाने के बाद. तो आप मतलब समझ गए होंगे जो नॉट फॉर नॉन अल्गेरियंस आई विश टू से, मेहंदी जब तक घिसती नहीं है उसका रंग आता नहीं है, इसलिए अपने आप को घिसिए और मेहंदी का जो रंग है उसको जाहिर कीजिए. All the best in every respect to all of you, especially for our guests who are from outside the campus. All the best, do well, work hard. Thank you very much.
Bhagya sir and Mohsin sir, do you like to share your views on the program? Please welcome Bhagya sir.
People on the dais and students message. When we reached Aligarh bus stand, we received a very warm welcome from Professor and for people in joining us in his team. And also we received a very comfortable accommodation. Food, I become very healthy now. And everything is very good here. So I am very happy. I wish for future program, next program, we are going to. So we will be very happy to participate here also. So both thanks.
Thank you very much. Good afternoon, everyone. I am really very thankful to all of you to see here to attend such a very important program. And for us people, for retired people, it is also very good. Sometimes we feel whenever we are with younger people, we also feel younger. It is very nice. It was very successful program, and I hope that in future also we would have such good people. So thank you very much.
Now finally the focus is on the participants. Anybody from you guys who want to come and share their views on the program? Anybody willingly? Anybody wants to come? Then maybe I have to call them by their names. I first like to request Dr. Naren sir to please come and share your views, sir.
Good afternoon, all of you. First of all, I would like to thank Department of Mathematics, Aligarh Muslim University, and especially its organizer of the workshop, Dr. Javed Ali sir, to provide us this opportunity. And we all of us might have attended such courses elsewhere also in other institutions, but this 1 week program was a turning point, will be a turning point. I think because this was totally focused on our research work, in which we are either working or we will do the work, and some new scopes, some new spaces, which personally I was not aware of, modular space and normal structure, all these things. So our main speaker, Kamsi sir, he told us how to teach also. Though I am also a faculty member in a department, and in our college students say that I am a good teacher, but first of all I was convinced that how a person can teach, how should we teach, and he is one of the best example. And the whole program was well decorated also. Well planning, lecture one by one, and at last the relational fixed point theory by Imdad sir also. And all the program, all the lectures were well organized, The hospitality point of view, if you think that all participants, I think all are well satisfied with everything. So thank you for everything also. Thank you.
Now I would like our PhD scholars, whoever wants to come and express their views, whoever wants to come. Wakar bhai, you come please.
Thank you inviting for us. Good afternoon to all of you. I am here to present our view on this GIAN course, the fixed point problem, the old and new. To attending this conference on this topic is very really great experience. The exchange of knowledge and insightful discussions have been invaluable, and this program also provide an excellent platform for all researchers and scholars and experts from various fields, and surely the knowledge gained from this event certainly will contribute to our academic and research work. And in the last, I want to, on the behalf of our league community, I welcome all the participants and heartfelt gratitude to all the participants across the India and the guests, especially Hamsi sir from Khalifa University, Dubai, and University of Texas, as well as to my department, and especially the course coordinator Dr. Javed Ali sir to organize wonderful event. Okay, thank you.
Now I would like to invite Dr. Izharuddin sir to please share your views.
Good evening, everyone. And I am thinking that I am the participation. I was thinking that I am of the one of the organizing team. So first of all, congratulations to Dr. Javed Ali for this GIAN program. And I can take lots of participation from different corner of the country has come. So in my view, the conference has at least two motivation. Number one is the academic exchange. So the last 5 days we have seen lots of academic exchange between you and an expert, as well as the between among you people. And the second view is that the cultural exchange. So even I have spent the 11 years at this university, I never visited the museum of the library. So thanks for arranging the visit to the library. So this is all the very good cultural exchange. And also I visited the first time the Sir Syed Academy. So thanks Javed Ali sir for organizing this. And also because of the limitation at the accommodation and other facility which other institute have. So if there is any lacuna or any at this part, so I am also as being the senior of my research scholar team, so I am also apologizing for anybody and for any inconvenience, either the stay, either the food. So special, I could find two friends during this GIAN program. One is Arpit Kansal. I did not know much about him before, but we had a very interesting conversation yesterday. So, and one of the most important thing is that the research scholar of this department, they were standing for every fraction of second for every part. So I especially request Dr. Javed Ali, kindly give the at least one specialty party to them. So thank you.
Okay. Now I'd like to call upon Arpit Kansal to share his views.
Okay, good evening everyone. Professor Khamsi, can I use my assistant? Okay, so I would like to thank everyone, organizers, speakers, for organizing this wonderful seminar. It was really wonderful to attend all the lectures. I mean, for someone who works in operator theory like me, it was my first formal interaction with the fixed point theory. I loved learning. I'll not say I learned all the techniques, but whatever I learned, it was really beautiful. And of course, if I can be a little greedy and can suggest something. So I wish the lectures were a little more arranged chronologically so that at least for person like me who could have understood little more than what I have really gained from here. And probably I would love to be here again. Thank you. Thank you, everyone.
First of all, good evening all. I would like to share my personal experience with this GIAN course to begin with. Thank you. First of all, I would like to thank Aligarh Muslim University and the course coordinator, Dr. Javed Ali, for conducting such an enlightening course carrying over a period of 5 days. And it doesn't feel, as Professor Khamsi said, it never feels complete. And I'm already longing for the second part of this course, and only thing I would like to know now, when is it going to be? So yeah. So that's it. I'm a very young researcher, maybe only 1.5 years into research in this area, fixed point theory. I'm still learning a lot of things every day. Day by day I'm learning a lot of new things, and for me last 5 days gave several ideas or directions with which I can move forward, and I hope it helps me take forward research in my own way. Thank you so much. Thank you, sir.
We also have participants from South India.
Maybe more.
Who's from South India? Can you please guys raise your hand? Anybody from South India?
Yeah,
you were from South India. Yeah. Okay.
Maybe.
Anybody else?
Srinivasan, maybe you.
Do you want to come and share?
Anyone. If you want to share.
Not only about this program, but also about your stay and everything. We want to know.
Very good afternoon to everybody. First of all, I'm grateful to Javed Ali sir and Aligarh Muslim University for conducting such a wonderful program. When he was presenting the report, he was saying a long 5 days, but I feel it was a short 5 days because we didn't yet covered a lot of things in fixed point theory. As a beginning research scholar in fixed point theory, I was thinking like I'm doing something new in fixed point theory, but after coming here and after hearing all the lectures from here, I think I'm still in the old fixed point theory. so I have to do something new in fixed point theory. I mean, in the so-called new fixed point theory. So I'm requesting Javed sir for conducting the next level of this GIAN program. So thank you everybody. And as she was mentioning, the stay, the food, everything was good, and all the facilities given. I'm thankful to Javed sir and all the research scholars who was working behind. This program was conducted very nicely. Thank you for that also. Thank you very much.
Thank you so much. So last but not the least, I would like to call upon the local GIAN coordinator, Professor Vibha Sharma, to present a vote of thanks.
Professor Khamsi, Professor Shahid Ali, Dr. Javed Ali, Professor Chaudhary, Professor Khan, Professor Dhage, Professor Bursalim, Professor Imdad, Professor Shamsul Hayat, participants from across India, research scholars of Department of Mathematics, faculty members. It is indeed a matter of privilege for me to stand here and do the easiest task in this room, that is to just come and say thank you and bid you adieu. But I think as the local coordinator for GIAN course, all the boxes are checked for me. Very good feedback from the participants. Everybody is going back with good memories, and there are demands for the next level of course. So nothing can be more gratifying for me as the local coordinator who represent Aligarh Muslim University. So in my capacity as the local coordinator, I did a bit of it when I introduced the concept of GIAN in the opening session. And since it is a closing session, I must say a few words about my university, because that's what this course also stands for. So especially people who have come from different cities and different parts of this country, and Professor Khamsi, I would like to have your attention to the fact that our university is one of the grand old institutions of this country, and we are the path breakers who have shaped the academic makeup, research makeup of this country for more than 100 years. And in 21st century, it's very proud fact for me to say that we are competing with new institutions, we are competing with privatized institutions, we are competing with new arenas of research with equal energy and conviction that we did 100 years ago. And this particular program's success, the two words, especially the old and the new, represent that. We know that we are good in offering the old, but we know that we are definitely the place where the new will happen very soon. So I'm very happy that all of you are having this unsatiated desire that good should have been served more. The new should have been served more. तो इस तिश्नगी के साथ आप लोग वापस जा रहे हैं. The desire, the unsatiated gratifying desire. So thank you very much. I thank each one of you, especially for those who have come to Aligarh. I hope your stay was pleasant. If there was anything that we could not do up to your expectations, then I take this on my part, and apologies, please accept my apologies for that. I am thankful to the Department of Mathematics for being the flag bearer of our hospitality and our academic tradition. I especially thank our Vice Chancellor for being a true leader and leading us by example by always being there for the matters of research, for the matters of academic nature, and she always has yes to say for such things. I'm thankful to all the functionaries of this university for facilitating this program. And last but not the least, I'm very, very much thankful to all the students of this department for being so enthusiastic and so forthcoming along with their teachers and working day and night, running pillar to post to make this program, where 62 participants have been there, a great success, a grand success. So when you go back, please take it from us that we will meet again under this roof once again. Happy journeys back home, and please remember AMU in your good wishes. Thank you very much.
Okay, so now we are almost close to this program. Of course, Professor Via ma'am already thanks to all dignitaries and all the functionaries of university. But I also mentions to my special thanks to my colleague and friend Izharuddin. He was almost along with me in every step, and my research scholar Faraz and Junaid and Shadan and other scholars also. Whenever I call for any task, Vijender is there, Wajahat is there, Hifzur, Ayub, and So maximum all students Bakar, so all students are, my students are very friendly. Of course they are working, but they are always ready for any task for me. So this is very important for successful conduction of any program. So with these words, I say Alvida, and now it's a time for tea. Thank you very much with us. So let us have tea. Maybe outside. So just one picks, just in the that glass. Yes, those who don't collect their certificates, certificates are ready, so they can collect. And local students can collect the certificate later. But only
पानी पिला दो थोड़ा सा आधा बचा देता हूँ